Recording now. Okay, so major announcement, Math 231 final is on December 21st from 8:30 p.m. to 10:30 p.m. Okay, reminders, test 2 is on December 2nd in class on Zoom. The review for test 2 is today. We also have test 3 on December 9th, and the review for test 3 is on December 7th. Okay, so these are all the reminders, and this is the final. Okay, so you now know when the second and third exams are, the reviews, and the final. Okay, so I gave you a video to watch since last class, right? Lesson 25 video. Okay, and so on that, I finished chapter 4. And so we've covered all the material for test 2 before the start of this class. Okay, anyone have questions about any of these problems? All these problems I gave? Anyone have questions about them? I'm going to give a review today for test 2. So after we cover the material I want to cover, we'll spend the rest of class reviewing, which can also be homework problems and can be review problems. Okay, so the faster I get through the material I want to cover for today, the more time I can give you for the review. I'm also willing to make class longer if you want. And so if class is longer, I'm willing to extend the review further. It's recording now, so it's whatever we do will be on YouTube, and so you'll be able to watch it after I post it. And so if you have to leave right after class or soon after, you don't stay, I'll have the recording up. And so if it's extended, you'll see whatever I do. Okay. If you have questions, please ask. Okay, so there's no questions on homework. Let's go. We can go back to that later. I just need to cover some material. I covered a bunch of problems at the end of last class, so I even included them here. These are the same problems we did at the end of last class. Okay, so I'm going to continue right where we left off last class. Okay, so the next theorem is theorem 5.2.2, which part A says if lambda 1 to lambda k are distinct eigenvalues of A, and if v1 to vk are corresponding eigenvectors, then v1 to vk is the set is linearly independent. Okay, so if you have distinct eigenvalues of a matrix and you have corresponding eigenvectors for those distinct different eigenvalues, then those eigenvectors form a linearly independent set. Okay, and part B says for an n by n matrix with n distinct eigenvalues is diagonalizable. Okay, so if you have an n by n matrix with n distinct eigenvalues, then it is diagonalizable. Okay, remember, if you have an n by n matrix A, the meaning of it being diagonalizable is saying that there is some matrix P such that P inverse AP is a diagonal matrix. Okay, so this is a procedure for diagonalizing an n by n matrix. Step 1, find a basis for each eigenspace and count the total number of vectors. If you found n, then the matrix is diagonalizable. If not, then the matrix is not diagonalizable. Okay, so what does this mean? You have to find the eigenvalues for your matrix. You have a matrix and you find its eigenvalues, all of its eigenvalues. Okay, for each eigenvalue, you have a corresponding eigenspace. Okay, so for each eigenvalue, you have a corresponding eigenspace. That eigenspace is a vector space. It has a basis. And so for each eigenvalue, you have an eigenspace with a corresponding basis you can find for it. And so you have the basis vectors in that basis. So for each eigenvalue, by this process so far, you have a collection of basis vectors for its corresponding eigenspace. So as you go through all the possible eigenvalues, for each one you have eigenvectors. You have basis vectors. Count all of those vectors. If the total is n, where your matrix is n by n, if the total is n, then the matrix is diagonalizable. And if the total is not exactly n, then it is not diagonalizable. If the matrix is diagonalizable, then form this matrix P, whose column vectors are the n basis vectors in step 1. So the first column is the vector P1. The second column is the vector P2. The third column is the vector P3, ... the last nth column is the vector Pn, okay? You need n vectors to form an n by n matrix from them, right? If you didn't have n vectors, you couldn't form n columns from less than n vectors. You need n vectors to do step 2. So that's a hint. If you get to step 2 and you don't have enough vectors, that means you may have reached the wrong conclusion in step 1. Okay, so these p's are the basis vectors you found in step 1. Okay. Step 3 is P inverse AP is a diagonal matrix whose successive diagonal entries are the eigenvalues lambda 1 to lambda n that correspond to P1 to Pn. So what does that mean? In step 2, we form this matrix P. And so given this matrix P, if you take its inverse P inverse, then multiply by A, then multiply by P, you get a diagonal matrix. A diagonal matrix is a matrix whose only entries that are non-zero can be on the main diagonal. Everything outside the main diagonal is 0. You could have zeros in the main diagonal also. But now, in addition, what 3 is saying is that you have a diagonal matrix whose successive diagonal entries are the eigenvalues of your matrix. Okay, so now the entries on the main diagonal are the eigenvalues, and those eigenvalues correspond to the basis vectors you chose in step 2. So if you change, you chose the order of these vectors, column vectors, right? Step 2 doesn't tell you you have to put them in a certain order, but once you put these vectors in a certain order, that will determine the order of the eigenvalues that will appear on the main diagonal of P inverse AP. Okay, so if P1 was a basis vector corresponding to the eigenspace corresponding to lambda 1, then your first entry in the main diagonal would be lambda 1. If P2 was a basis vector for the eigenspace corresponding to also lambda 1, then the next one will also be the same value, right? So these basis vectors and these eigenvalues corresponding to each other. Okay, so this could be a little difficult to get, but it's this procedure. So I put these 2 lines here. So in order to diagonalize the n by n matrix, you have to do what's in between these 2 horizontal lines. Nothing. So you just look at that. Okay. You may have to read other material to understand what this is saying, but the steps are completely in these 2 horizontal lines. Okay. If you know how to do these 3 steps correctly, and you do them, you're done diagonalizing an n by n matrix. So example 1 is find the matrix P that diagonalizes this matrix A. Okay. So we're going to be looking at this procedure for this example. So in the solution, the first thing you do is you find the characteristic equation of that matrix A, right? That's the equation determinant of lambda I minus A is equal to 0, right? So when you solve that equation for lambda, you get lambda minus 1 times lambda minus 2 squared equals 0. That's the characteristic equation of a matrix, right? And so now we have an equation with lambda. So you can solve for lambda. So the 2 possible, well, you can see right away. The 2 possible values of lambda are lambda equals 1 and lambda equals 2. Okay, so that's why you're finding the characteristic equation. You want to find all the eigenvalues of your matrix. The eigenvalues are all the values of lambda that satisfy the characteristic equation of your matrix. So lambda equals 1, lambda equals 2 are all the eigenvalues of this matrix A. For each of those values, lambda equals 1, lambda equals 2, there is a corresponding eigenspace. Okay, and so what we want to do is we're going to start with lambda equals 2. And for lambda equals 2, we want to find the eigenspace corresponding to lambda equals 2. And we want to find a basis for that eigenspace. Those basis vectors that make up the basis for the eigenspace corresponding to lambda equals 2, those are going to be the vectors we're going to use to form the matrix P in step 2. These P's, these column vectors, are basis vectors of eigenspaces. Okay? So when lambda equals 2, you want to find the eigenspace corresponding to lambda equals 2. The eigenspace corresponding to lambda equals 2 is the set of all vectors x that satisfy the equation that I have bolded here. The equation 2i minus a times x equals 0. That's because you want lambda I minus a times x equals 0 and lambda equals 2. So I substituted lambda equals 2 here. That 2 is lambda, and here lambda is 2. So the set of all vectors x that satisfy this equation is the eigenspace corresponding to lambda equals 2. Okay? And so we want to find that space. And so when you find that space, you can find a basis for it. You just solve a linear system like you normally would, and you find all of its solutions, and you find a basis for that solution space, and you get that these two vectors form a basis for the eigenspace corresponding to lambda equals 2, -1, 0, 1, and 0, 1, 0. So with this basis for the eigenspace corresponding to lambda equals 2, we have two basis vectors, P1 and P2, the two vectors in that basis. Okay? These two we're going to choose them as the first two columns of our matrix P, which will diagonalize our starting matrix A. Okay? We're finding a matrix P, we're creating a matrix P that diagonalizes A. It's a matrix P such that P inverse AP is equal to a diagonal matrix. And the entries on the main diagonal of that diagonal matrix are the eigenvalues of your matrix that correspond to the eigenvectors you chose as columns of the matrix P. Okay? Okay, but so for lambda equals 2, we have two basis vectors for the corresponding eigenspace. With lambda equals 1, we have the eigenspace corresponding to lambda equals 1. That's the set of all x values such that 1i minus a times x equals 0. So we want to find all possible values of vectors x that satisfy this equation. That's the eigenspace corresponding to lambda equals 1. That space is the set of all scalar multiples of that single vector. And so a basis for that eigenspace is just the span, is that single vector. That's a basis for it, right? And so we have another basis vector for now this other eigenspace. We have another basis vector P3, which is -2, 1, 1. So we have now found three basis vectors, right? And we've now exhausted all possible eigenvalues for a matrix. There are only two, and we found all the basis vectors we can for each. Our original matrix was a 3 by 3 matrix. So here n is 3. And so we found three basis vectors. So in step 1, we found n. We started with the 3 by 3 matrix, and we found three eigenvectors. And so that means the matrix is diagonalizable. And so we can go to step 2, and we can find a diagonal matrix P that diagonalizes it. So this matrix P that diagonalizes A, we can form it from these basis vectors as the columns of the matrix. So the first column of this matrix is our first P1. P1, -1, 0, 1, that's the first column. P2, which is 0, 1, 0, is the second column. And P3, which is -2, 1, 1, is the third column. So we now made a matrix P that diagonalizes A, meaning that P inverse AP is a diagonal matrix, which it is. And so if you take P and you take its inverse, P inverse, then multiplied by A, our starting matrix, then multiplied by P, the product of those three matrices will give you this diagonal matrix, where the diagonal entries are 2, 2, 1 in that order. Okay? And so see how our first two basis vectors were basis vectors for the eigenspace corresponding to lambda equals 2. And in our diagonal matrix here, the first two entries on the main diagonal are 2, corresponding to lambda equals 2. Our third basis vector, P3, was a basis vector for the basis of the eigenspace corresponding to lambda equals 1. And so when we get our diagonal matrix at the end, in the third column, the entry on the main diagonal in the third last column is a 1. And that's no coincidence. It's because we chose P3 to be the third column, and that P3 was a basis vector for the eigenspace corresponding to lambda equals 1. Okay? So actually, without multiplying this, if you've done everything up to this point correctly, you know the answer without multiplying these matrices. It has to be 2, 2, 1, because this is lambda equals 2, lambda equals 2, lambda equals 1. Okay, see that? So you get this answer without even doing all the work of multiplying. Order of column vectors of P does not matter. What I mean by that is that we could have, instead of this being the first column, this second, and this the third, I could have rearranged these three columns, and it would have gotten another matrix P that still diagonalizes A. The only difference is that when I do P inverse AP of this different matrix P, where the columns are in a different order, then the entries on the main diagonal will be in a different order. They will be in an order corresponding to the new order of columns I chose for my new matrix P. Okay? So you can choose any order you want for the columns, but that will determine a different diagonal matrix at the end. But the method will be the same. The entries will correspond to the basis vectors and the eigenspaces they correspond to. Okay, note, a triangular matrix with distinct entries on the main diagonal is diagonalizable with eigenvalues, those entries on its main diagonal. Okay, so if you have a triangular matrix with distinct entries on the main diagonal, you have distinct eigenvalues. Okay, and so you have the number of eigenvectors is the size of the set, is the number of columns. Okay, each one has its own eigenvector, and so you end up with enough to get a diagonal matrix, diagonalizable matrix. Theorem 5.2.3. If k is a positive integer, lambda is an eigenvalue of a, and x is a corresponding eigenvector, then lambda to the k is an eigenvalue of a to the k, and x is still a corresponding eigenvector. Okay? So even though you're considering the matrix a to the k, and the eigenvalue is raised to the kth power, the corresponding eigenvectors stay the same. So the corresponding eigenvectors do not change, just the eigenvalues change. Okay. Okay, so in example 6, we want to find a to the 13th power, where matrix A is this 3 by 3 matrix here. Okay, so in our last example, we had the same matrix A. Okay, so we're going to use some of the results of the last example to do this problem. So from our last example, we have that this matrix P diagonalizes A. This was our matrix P at the end that diagonalized A. And D, which is P inverse AP, is equal to this matrix. Okay, so we're going to use both of these things. So since this matrix, this is D, that's the matrix D. Since D is equal to P inverse AP, if I multiply both sides on the left by P and both on the right by P inverse, I get that if I can solve for A here and write A is equal to P times D times P inverse. So looking at this equation, you can solve for A and get A is equal to P D P inverse. Okay, so I want to find A to the 13th power. So by substitution, I can substitute A for PDP inverse. So A to the 13th power is PDP inverse raised to the 13th power. Now, if you multiply this by itself 13 times, notice that the P's and P inverses cancel in the middle. If you PDP inverse times PDP inverse times PDP inverse, the P inverses and P's cancel. When they cancel, this thing would cancel with this, right? And then this thing would cancel with the next P. This would have canceled with the previous P inverse. All these red things in the middle would disappear, but the D's would then become next to each other. This D, when the P inverse and P cancel, then the next term after that D will be the next D, and then the next D up to including the last D. So these D's, instead of being separated by P's and P inverses, the P and P inverse cancels each other out, and we have 13 consecutive D's multiplied by each other. And so at the start point, we have a P, and at the end, we have a P inverse. So the product of P D P inverse raised to the 13th power is P times D to the 13th power times P inverse. The red terms go away, and we're left with the blue D's. We're left with that. And then at the beginning, we still have P here. This does not cancel with anything, and the P inverse at the end does not cancel with anything. And so we have that P at the beginning and this P inverse at the end. Okay, so A to the 13th power is P D to the 13th power P inverse. So this is P from the last example. Then you take the diagonal matrix D, this is D, you raise it to the 13th power. So it's that matrix raised to the 13th power, then times P inverse. Well, you take the inverse of this matrix P, you'll get this matrix. Okay, well, when you take a diagonal matrix and you raise it to a power, then it's equal to the matrix, diagonal matrix, where you just raise the diagonal entries to that power. So this matrix to the 13th power is this matrix where you have 2 to the 13th there, 2 to the 13th here, and 1 to the 13th there. Okay, you still have the same matrices on the left and right of it. So you take 2 to the 13th power, 2 to the 13th power, and 1. That's 1. And then you do all this multiplication. And after you do all this multiplication, you get this matrix. So that's the matrix A to the 13th power. Okay? And so in order to get a to the 13th power, we diagonalized a. Okay, so we're able to express a as p d p inverse, where d is the diagonal matrix. Okay. Okay, so then we substitute a for that and then calculate it. Definition: if lambda naught is an eigenvalue of n by n of an n by n matrix A, then the dimension of the eigenspace corresponding to lambda naught is called the geometric multiplicity of lambda naught. Okay, so for each eigenvalue of your n by n matrix A, there is a corresponding eigenspace. It's a vector space, right? So each eigenvalue has a corresponding eigenspace, which is a vector space, which has a dimension. The dimension of that corresponding eigenspace is the geometric multiplicity of your eigenvalue lambda naught. So for each eigenvalue, you have a corresponding geometric multiplicity of that eigenvalue. Okay. So that's called the geometric multiplicity of lambda naught. And the number of times lambda minus lambda naught appears as a factor of the characteristic polynomial of A is called the algebraic multiplicity of lambda naught. So when you find the characteristic polynomial of a matrix, the determinant of lambda I minus A equals 0, right? You get an equation, and on the left side, you have a certain number of factors of lambda minus lambda naught. The number of times that factors into the left side, that's called the algebraic multiplicity of lambda naught. Okay, so for each eigenvalue, you have a geometric multiplicity and an algebraic multiplicity for each eigenvalue of a matrix A. Theorem 5.2.4. If A is a square matrix, then A, for every eigenvalue of capital A, matrix capital A, the geometric multiplicity is less than or equal to the algebraic multiplicity. Okay, so the geometric multiplicity is always at most the algebraic multiplicity. It can never be greater. Part B says A is diagonalizable if and only if the geometric multiplicity of every eigenvalue is equal to the algebraic multiplicity of that same eigenvalue. Okay, so before we said A is diagonalizable if you have n eigenvectors. Okay, and so it's like that. The only way you have n eigenvectors is if the geometric multiplicity of each eigenvalue is equal to your algebraic multiplicity of that same eigenvalue. Okay. Okay, so right, because the dimension of your eigenspace is the number of eigenvectors you're getting when you find a basis for the eigenspace, right? So your geometric multiplicity is like the number of basis vectors you're getting. And so in order to have a diagonal matrix, you need to have a total of n basis vectors at the end. It's the only way you can have a total of n is that for each eigenvalue, you have enough basis vectors that covers, in a sense, the amount of space that eigenspace is taking up. So, you need this to be equal to the algebraic one. Okay. So the last section in chapter 5 is section 5.3, which is on complex vector spaces. If z equals a plus bi is a complex number, then the following. So the first thing, the real part of a complex number here is a, that number, and the imaginary part is b. These are the real and imaginary parts of z, respectively. This is called the modulus of z. Or the absolute value of z. That's equal to the square root of a squared plus b squared. Z bar is the complex conjugate of a complex number z. It's equal to a minus bi. Okay. I'm going to go to the whiteboard and just draw something here. So if you have, okay, so here's the real part, and this is the imaginary part. And so if you have, let's say, a real number, let's say this is 1, this is I, this is 2i. Okay, let me just. Okay, good. Okay. So then let's say we take that's 2i. Okay, so we take this point right here. This is z, which is equal to 1 plus 2i. And it corresponds to a point in the xy plane where the x component is your real component, which is 1, and the imaginary component is 2. Okay, but z is equal to 1 plus 2i. Another example would be, let's say you had, this was 3. Let's say you had this point here. And so let's say you had, call this z2, which is equal to 3 plus I, or 3 plus 1i. And the real part is 3, and the imaginary part is 1, because you're adding 1i, right? It's z1, and the other one's z2, right? In general, you have a complex number z, which is equal to a plus bi. The a is the real part, and the b is the imaginary part. Okay, a and b are real numbers. Okay, so that's okay. So then another things I said. So I also said they talked about the modulus or absolute value of z. So the absolute value of z is the distance of this point from the origin. So the distance of that line segment is the absolute value of z1. The length of this segment here, the length of this segment, right? Okay, so the length of that segment would be the modulus of z2. Okay, and so the modulus of a real number is just equal to the square root of a squared plus b squared. It's using the Pythagorean theorem and finding the length of the hypotenuse of your triangle, right? So for instance, in the purple triangle, right, you had, this was length 1, and this was length 2. And so if you want to find the modulus of z1, it's just the length of the hypotenuse of this right triangle, which is the square root of 1 squared plus 2 squared, the square root of a squared plus b squared. And here, the hypotenuse is the modulus of z2, where the length of this side of the right triangle is 3. You have a right triangle, and the length of this side is 1. And so the modulus of z2 is equal to the square root of 3 squared plus 1 squared. Okay, and so that's the modulus or absolute value of a complex number. Okay, that's this one. The third thing is the complex conjugate of z. So if z is equal to a plus bi, z bar is a minus bi. It's just a reflection of your point z by the x-axis. So if you start with this purple point z1, then its conjugate z bar would be reflecting that z1 about the real axis. So the real component would stay the same, but you would negate the imaginary component. So this would be 1 minus 2i. Its modulus would stay the same, but it would just be reflected about the x-axis. So z1 bar is that, and z2 bar is reflecting z2 by the x-axis. And so z2 bar has the same real component, but the negative of the imaginary component. And so the effect of negating the imaginary component is the same as reflecting the point that represents the complex number about the x-axis. Okay, so that's okay, and so that this is the modulus. Right, that's good. Okay, so that's z2 bar. Okay, so you're just reflecting z2 about the x-axis to get z2 bar. Okay, and so z bar, if z is a plus bi, z bar is a minus bi. Okay, so now if you take a complex number z and multiply it by its conjugate z bar, the effect is that you get the modulus of z squared. You get a squared plus b squared. Okay, so if you take, let's say you take this complex number z1 and multiply it by its complex conjugate z1 bar, the value of z1 bar is equal to the modulus of z1, that length. Okay. Right, if you do 1 plus 2i times 1 minus 2i, that's z1 times z1 bar. The effect is 1 plus 2i minus 2i, and then minus 4i squared. The 2i and negative 2i cancels. And so you get this is equal to 1 minus 4i squared. Very important. I squared is equal to negative 1. Okay, so if I squared is equal to negative 1, this is equal to 1 minus 4 times negative 1, and that's equal to 5. 4 plus 1 plus 4 is 5. So this times this is 5, and if you compute the modulus of z1, it's 5. So the modulus of z1 is equal to the square roots. Oh, sorry, the modulus of z1 squared is equal to 1 squared plus 2 squared, which is 5. Okay, so the formula I wrote down on the other board is that z bar is equal to the modulus of z, or absolute value of c, squared. Okay, and so that's what we get here. Okay, z bar is equal to modulus of z squared. Phi is the argument of z. So phi is the angle that the angle that between the x-axis and this line from the origin to your point. So here, this is theta. I'll call this theta 1. Theta 1 is the argument for z1. It's the angle that this line segment makes with the x-axis. And I'll call this theta 2 for z2. And maybe I'll use the same color green. This is theta 2 for z2. The angle that this line segment makes, the blue line segment makes with the x-axis, that's theta 2, and that's the argument of the complex number z2. Okay, it's an angle. Okay, so that's called the angle. So sometimes you use phi and sometimes you use theta. So you interchange with theta and phi. So I wrote phi in the other, so I'll write phi here. So this is phi 1. This is phi 2. Okay. That's the argument of z1 and z2 respectively. Okay, so phi is the argument of z. And so if you take the real component of z, you can express it as the modulus of z times cosine phi. And the imaginary component of z is equal to modulus of z sine phi. Okay, so what does that mean? So I'm going to go to another picture now to illustrate this. There's too much going on in that other picture. So let's say you have the x and you have the real and imaginary component. You have the real component for here, and you have the imaginary components here. And so let's say you have a complex number right here. Okay, so you want to express the real and imaginary components of z in terms of the argument of z, the angle phi. So let's look at a circle centered at the origin that goes through that point z. Okay, so this is a circle centered at the origin that goes through that point z. There's only one circle centered at the origin that will go through a fixed point on the plane, right? Okay, so that circle has a radius, and that radius is the modulus or absolute value of your complex number, right? So that radius there. Now, if you look at the x coordinates, z is equal to x comma y, where x is its x coordinate, y is its y coordinate, right? So here is x and here is y. So if this is the argument of your complex number phi here, then this x, this distance here, is equal to this distance is the modulus of z, or that radius, times cosine phi. And this y distance is the modulus of z, or absolute value of z, times sine phi. Phi is the argument of that complex number. Okay, and so the x component is the absolute value of z cosine phi, and the y component is absolute value of z sine phi. So x is equal to absolute value of z cosine phi, and y is equal to the absolute value of z sine phi. Okay. And so sine and cosine are trig functions that tell you the ratio of the sides of a right triangle. Just put a dotted line here. I guess I'll put a dotted line here. Okay, so cosine of this phi is the ratio. Cosine of phi is the ratio of the adjacent side, which is length x, divided by the hypotenuse, which is the modulus of z. That length is the modulus of z. Okay, so this length is the modulus of z. That's what it is, right? So cosine of phi, that angle, is the ratio of the adjacent side, which is x, divided by modulus z. And so from that, you get that the x is equal to, modulus of z cosine phi. Okay. And then if you do the trig function for sine phi is the ratio of the opposite side, which is y, divided by the hypotenuse, which is modulus z. Remember, when you're doing trig, there's the acronym SOHCAHTOA. And so SOHCAHTOA tells you how to find sine, cosine, and tangent, right? Sine is the opposite over the adjacent. Cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So for cosine, we already had adjacent to the side, the leg adjacent to the angle, divided by the length of hypotenuse. And then for sine, we have the opposite. And then see the opposite, the length of this thing, right, is the height, which is y, right? That's y. Okay, so the opposite side is y divided by the hypotenuse, which is modulus z. And so that tells you that y is equal to, by cross multiplication, y is equal to modulus z times sine phi. Okay, so that's how you get that x and y are those things. Okay, so x is the real part of z, and y was the imaginary part of z. So you're getting those two equations there. So z is equal to x comma y, in this case, modulus of z times cosine phi plus I sine phi. This is called the polar form of z. Okay, and so this is how I'm getting this. So x, so z is equal to x is equal to, I'm going to x plus iy here, or a plus ib here, x plus iy. This is equal to modulus of z cosine phi plus I times modulus of z sine phi. So now you just factor out the modulus z. So if you factor out the modulus z, you get modulus of z times cosine phi plus I sine phi. Okay, so z is equal to modulus z times cosine phi plus I sine phi. That's the polar form of a complex number. Okay, so you can determine where a point is by its distance from the origin and the angle that 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 segment makes with the x-axis. Okay, that's another way of locating a point on the xy plane. You can either know its x distance left or right, then up down, or you can know its distance away from the origin and the angle from the x-axis, oriented counterclockwise. Okay, so definition 1, if n is a positive integer, then a complex n-tuple is a sequence of complex numbers v1 to vn. Okay, so the set of all complex n-tuples is called complex n-space, known by Cn. Okay, so Cn is the set of all complex n-tuples. It's the set of all ordered lists of n complex numbers. It's the set of all ways to list n complex numbers. That's Cn, complex n-space. It's called complex n-space. Scalars are complex numbers, and the operations of addition, subtraction, and scalar multiplication are performed component-wise. So example 1, let v equal to this vector 3 plus I, negative 2i, 5. The components, instead of being real numbers, are complex numbers. Numbers of the form a plus bi, right? Where a is the real component, and b is the imaginary component. Okay, so this is a vector, a list of 3 complex numbers. This is a 3-tuple of complex numbers. This is a complex 3-tuple. And let's say the matrix A is this one. But this is a complex valued matrix A, where the entries of the matrix are not real numbers, they're complex numbers. So each entry is a complex number with a real component and an imaginary component. Then V bar. So if you take the complex conjugate of a complex n-tuple, you just correspondingly take the complex conjugate of each component. So the complex conjugate of the 3 plus I is 3 minus I, and that's the first component. The complex conjugate of negative 2i is positive 2i, and that's the second component. And the complex conjugate of 5 is still 5, okay? Because 5 is 5 plus 0i. So the complex conjugate of 5 plus 0i is 5 minus 0i, which is still 5. So you can have the complex conjugate of a complex number be the same, not change, right? If you have a point on the x-axis and you rotate it about the x-axis, it stays where it is. Okay, so all real numbers, when you think of a real number as a complex number and you take its complex conjugate, it's itself. Okay, so the real part of a complex 3-tuple is just taking the real part of each component and making them the corresponding components of the vector real of v, the 3-tuple. So the real component of 3 plus I is 3. That's the first component. The real component of negative 2i is 0. And the real component of 5 is 5. And so real of v is that. And so this applies for any complex n-tuple. So if we had a complex 6-tuple, you would just find the real of v in the same way, but with 6 components instead of just 3. And the imaginary part of v, the imaginary part of this complex 3-tuple is just taking the imaginary part of each component and making them the corresponding components of Im of v. So the imaginary component of the first component, the imaginary part of the first component is 1. The imaginary part of the second component is -2. And the imaginary part of the third component is 0. So this is the imaginary of v. Okay, so I'm showing you how to find the real imaginary components of a complex n-tuple, how to find the complex conjugate of a complex n-tuple. This applies not just for complex 3-tuples, but again for complex n-tuples. Okay, now we have a complex matrix, complex valued matrix. If you take the complex conjugate of a complex valued matrix, you just take the complex conjugate of the entries and make them the corresponding entries of a bar. So the complex conjugate of 1 plus I is 1 minus I. The complex conjugate of negative I is plus I. The complex conjugate of 4 is itself 4. Complex conjugate of 6 minus 2i, 6 plus 2i. So that's a bar. Okay, this illustrates how to find the complex conjugate of a matrix, a complex valued matrix. And so if you take the real component of a complex valued matrix, you just take the real parts of the entries of the matrix and make them the corresponding entries of real of A. So the real part of 1 plus I is 1. The real part of negative I is 0. The real part of 4 is 4. And the real part of 6 minus 2I is 6. And those make up the components, the entries of real of A. Then the imaginary of A is similar. You just find the imaginary components of these entries, and they become the corresponding entries of the imaginary of A. So the imaginary part of 1 plus I is 1. The imaginary part of negative I is negative 1. The imaginary part of 4 is 0. The imaginary part of 6 minus 2I is negative 2. That's the imaginary part of a matrix A. That's complex value. And then the determinant of A, you find determinant the same you would find a real valued matrix. You take AD minus BC because it's a 2 by 2 matrix. And so you get 1 plus I times 6 minus 2I minus negative I times 4. And when you do that arithmetic, you get that equals to 8 plus 8I. Okay, so in this short entry here, I told you how to find these things. So when you're dealing with complex numbers, they're expressed in the form A plus BI. And so you would not express a complex number as I cubed or a multiple of I cubed. But you might, when dealing with complex analysis, you might be given I cubed and say, what is it as a complex number? You would then have to express it as a complex number, right? So if somebody gave you I cubed, then I'm not going to test you on this. If somebody gave you I cubed and said, what complex number is it? Well, this is equal to I squared times I. I squared is negative 1. So this is negative 1 times I. And so I cubed is equal to negative I. And so as a complex number, Z is equal to I cubed is equal to 0 minus I. And so we've now written it in the form we want it to. Does that make sense? So when you're looking at numbers like I cubed, you can still express them as A plus BI. And so that's how you would normally think of it. And so if you're looking at it geometrically, if you're looking at the point negative I, it would be here, right? So this point is also the point I cubed. Make sense? So negative I is that point right there, but I cubed is the same point. They're equal. So geometrically, I cubed would be where negative I is. Okay, so writing it in this way is much better. You can locate it better on R2, right? You can see where it is. You can't see where I cubed is necessarily, right? Just from looking at it. Okay, so okay, so that's good. So that's chapter 5. So I want to mention this stuff in this section briefly. We're not really talking that much about complex vector spaces in this class. Okay, so the most I would ask you about this on the test would be something like find A bar or find B bar or find the real part of B or the imaginary part of B. Okay, so when studying this section, if you know this brief part that I said here, you know everything you need to know about complex vector space. So I'm not going to ask you to convert I cubed into a complex number. Okay, so I'm not asking you those kind of things. It's just restricted to what I wrote down, this material right here. Okay, so next is chapter 6, 6.1, inner product spaces. So definition 1, an inner product on a real vector space B is a function that associates a real number given by this notation with each pair of vectors in capital V, such that for all vectors U, V, W in capital V and all scalars K, we have these following 4 things that happen. That word formatted this wrong. Okay, there, I fixed it. Okay, so if you take the inner product of U and B, it's equal to the inner product of B and U. So this is commutative. That's what it means. You can switch the order of the things here, and it doesn't change the value of the inner product. 2 says if you take the inner product of U plus V and W, it's equal to the inner product of U and W plus the inner product of V and W. 3 says if you take the inner product of KU and V, it's equal to K times the inner product of U and V. And 4 says that the inner product of V with itself is greater or equal to 0, and the inner product of V with itself is equal to 0 if and only if V equals 0. Okay, the word formats it. Okay, if it word format meant something else. Okay, so then a real vector space with an inner product is called a real inner product space. Okay, so I realize this is hard, right? So if you have a real vector space with an inner product, Okay, an inner product is a function. So a real inner product space is a team of two things. It's a real vector space and an inner product, which is a function. Okay, so an inner product space is a team of two things, a real vector space and a function. That's building on the fact that a real vector space is also a team of three things. So a real vector space is a team of three things. It's a set, an operation of operation of addition, and an operation of scalar multiplication. So a real vector space is a team of three things. You can think of that team as one object, one thing. That team is one thing. The Fantastic Four is one thing. It's a single team, right? So you have that team as a single object, and then an inner product space is two things: that team and a function called an inner product. Okay. So you're used to maybe thinking of names, giving things names individually or singularly, like you have a function, you have a number, right? But now we're defining things in terms of team. We're thinking of a collection of things and calling it one name. We're naming a team of things instead of just individual objects. Okay, so a real inner product space is a name of a team of two things, a real vector space and a function called an inner product. Those two things together make up what's called a real inner product space. If you remove one, it's not a real inner product space. Okay? And again, a real vector space is a team of three things: a set, like V, an operation of addition, and an operation of scalar multiplication, where 10 axioms hold, right? That's called and it's a real vector space when you're dealing with real numbers. Okay? These axioms are satisfied if the axioms meaning these four axioms. These axioms are satisfied if we define the inner product of U and V and Rn as this. Okay? So the definition of inner product is a function where these four properties hold for that function. Okay? There's lots of different inner product spaces. There's lots of different functions, teams with a real inner product space, right? And so this is an example of one such function that will satisfy all four of these properties, meaning that you can call it an inner product. Okay? So that function is this: if you take two vectors, U and V and Rn, a vector in Rn is an N-Tuple. It's a list of n real numbers, U1, U2 to Un, and vector V, a list of V1, V2 to Vn of real numbers, lists of real numbers. We're not doing complex numbers now. It's back to real numbers. So the inner product of U and V is multiplying the corresponding components of U and V. So the inner product of U and V here is U1, V1 plus U2, V2 plus ... plus Un, Vn. We call Rn, n space, with this inner product, the Euclidean inner product. Euclidean n space. Okay, so we call this function is called the Euclidean inner product. And then Rn teamed with this function is called Euclidean n space. Okay? So the team of the space, the real vector space, teamed with this function is the Euclidean n space. The function by itself is called the Euclidean inner product. Okay? It's an inner product because it satisfies all four of these properties. Okay? You have to prove it does, and you can, and you can. And so when you prove that this function satisfies these four properties, you prove that this function is an inner product. It's especially given the name Euclidean inner product because it's a special function. Okay? Definition. Wait, so going back here, right? I'm defining the inner product as a function that associates a real number with each pair of vectors in V. So what that means, visually, what that means is that if you think your inner product is a function, right? And this is called a machine diagram. So the name of your function is this given this symbol, okay? This is just the name. All the symboling is just a name. It's the name of a function where if you input two vectors, not one, if you input two vectors into it, U and V, the output is a real number. Okay? Well, that real number is equal to the inner product of U and V. Okay, so let me just put it like that. Okay, so I could name it that too, but maybe I'll just be very specific here. If I input two vectors in, the output is a real number, which is denoted by that symbol. Okay, so this thing is a symbol representing the real number you are associating two vectors with. Okay, So if you have, for instance, if you have the Euclidean inner product, okay, this is the Euclidean inner product. And you take two vectors. Let's say you take the vector 1, 1, and you take the vector 2, 2, 2, 3. And you input those two vectors into the Euclidean inner product. The output is a number, where that number, u comma v, it's a real number u comma v, which when you compute it, you get 1 times 2, the product of the first components, plus the products of the second component. 1 times 2 plus 1 times 3, which is equal to 5. Okay, so you input these two vectors into the Euclidean inner product function, and the output is 5. And this symbol, which confusing, I get this is confusing because I remember learning it. That's a symbol representing this number. Okay, it's not really the function, it's the number. Think of it as the number that you're getting. Okay, you're inputting two vectors u and v. So this is u here, this is the vector v here, and the output is a number denoted by that symbol, bracket u comma v. Okay, so that was just to help you visually understand what an inner product function is. Again, you pair that, you team that function with a real vector space, and you have an real inner product space. Definition 2. Definition 2. If V is a real inner product space, then the norm or length of a vector little v and capital V is denoted by that symbol. So this denotes the norm or length of a vector. Remember, a vector does not have to be a Euclidean vector. It does not have to be a physics-looking vector. A matrix could be a vector, and you can talk about the length of a matrix. Okay, vectors are just, a vector space is just something that satisfies 10 axioms. Okay, and so you can have very weird-looking things being vector spaces, and there are objects in them being vectors. Okay, and so if you have a vector space with all sorts of strange objects in them, you can talk about their lengths. Okay, and so this is defined by, we're defining the length of V as being the square root of the inner product of V with itself. Okay, with these definitions, all your pre-existing notions of length fit right in. So whenever you correctly calculate the length of something, like in physics of a vector, you could take that and put it into this more general definition of vectors and length, and it would give you the length of that vector. Okay, but now we're thinking of lengths and vectors more generally, and so now we can think of vectors, more things as vectors, so we think of the lengths of more things. Before, we can only find the lengths of physics vectors, and this can talk about lengths of many other things. Okay, so and the distance between two vectors is denoted by d of u comma v, and is defined by this symbol, which is the norm of u minus v. Okay, now remember, the norm of vector v is the inner product of that vector, the square root of the inner product of that vector itself. So you just apply that same principle here. If the distance between u and v is the norm of u minus v, then that's equal to the square root of the inner product of the vector u minus v with itself. Okay, now why is this true? Why is the distance between u and v equal to the norm of u minus v? Well, look at it visually. I'm going to use Euclidean vectors. If you take a vector u, this vector u, and you take this vector v, and you take remember, you can move a vector around and it's the same vector, right? But I'm going to make both these vectors start at the origin. So the beginning part is called the tail, and the end is called the tip. So I'm making the tails of both those vectors the origin. So if that's u and that's v, then you can talk about the vector u minus v. And so the vector v minus u. I'm saying u minus v. Okay, I'm saying u minus v there, so let's keep it the same. Okay, so u minus v would then be, it's going to go this way. This is the vector u minus v. Okay. You could use the tail tip method, and you could, if you're having trouble seeing why that's the vector, if you start at u and then you add negative v, right? This is negative v because it's the same magnitude and direction as v, but in the opposite direction. So if you start with at the origin, go u, and then you add negative v, the result is u plus negative v, which is u minus v. And that gives you the same vector. Gives you this vector right here. This is u minus v. Okay. And moving a vector doesn't change the vector. A vector is not defined by where it is. It's defined as its direction and magnitude. Okay, so if I just took that u minus v in the bottom left and I translated it to the other one, it's still the same exact vector. Okay, so u minus v is this. I'm really looking at the top one here. I'm talking about u minus v, this one. I was just showing you how I got it. So that's the u minus v I want to look at. Now, if I want to talk about the norm of it, then you're thinking of the distance between two vectors as being the shortest distance between their tails, their tips, right? You can think of that as the length of that vector. Okay, so so the shortest distance between them, if you start them at the same point, the origin, and you're at the tip of both these vectors, right? If you're looking at this point on the vector u and this point on the vector v, you want to talk about the distance between them being the shortest distance from one point to the other. And so that's the magnitude of u minus v. I mean, that's the length of u minus v. That's the length. Going in that direction is the fastest direction to get from one point to the other. And so that's how you define the distance between two vectors. Okay, so the definition, though it's weird, these definitions are very weird, they make complete sense. Okay, so a vector of norm 1 is called a unit vector. Okay, so a vector of length 1 is called a unit vector. Theorem 6.11. If u and v are vectors in a real inner product space V, and if k is a scalar, then the norm of v is greater than or equal to 0, with equality if and only if v equals 0. Okay, so that means the length of any vector is at least 0. You can't have a negative length for a vector. That's because of how we defined it. But it does match your intuitive notion of length and how length should not be negative, right? So the length is non-negative with equality if and only if v equals 0. So if you have a vector 0, its length is equal to 0. If you have a vector that's not 0, its length is non-zero. That's what that's saying. Okay. And now if you take the norm of a scalar multiple of a vector, kv, it's equal to the absolute value of the scalar k times the norm of the vector v. C, the distance between u and v is equal to the distance between v and u. Okay? And D, the distance between u and v is also greater or equal to 0. Okay? Whenever you talk about the distance between two vectors, it's always at least 0. And with equality if u equals v. So the only way the distance between two vectors is equal to 0 is if you're talking about the distance between the same two vectors. Once you have two distinct vectors, their distance has to be strictly positive. Okay, and note that this function defines an inner product on Rn called the weighted Euclidean inner product with weights W1 to Wn. So again, an inner product is a function that satisfies the 4 properties I listed earlier. So there's lots of different functions that satisfy those 4 properties. And so we had a Euclidean inner product that satisfied those 4 properties. Now we have another one called the weighted Euclidean inner product, where instead of doing u1, v1 plus u2, v2 plus dot, dot, dot plus un, vn, you multiply each of the products by a weight. So the first product you multiply by the weight w1, the second product you multiply by the weight w2, to the last product, which you multiply by the weight wn. And so now the sum of these products, where each product is a product of 3 things, this is called the weighted Euclidean inner product. It's a function that where if you input the vectors u and v, the output is this number. Okay, this is again word fixed it, it's equals. Okay, so the inner product of u and v equals that sum of products. Okay, definition 3. If V is an inner product space, a team of an inner product function with a vector space, then the set of points in V that satisfy the norm of U is equal to 1 is called the unit sphere or unit circle in V. Okay, if you're in R2, the unit sphere in R2 is a circle. Or, well, you might think that it's a circle. Then, okay. Technically, though, a unit sphere or a unit circle doesn't have to be a circle. Okay, it's just a name. Okay, by the way we're defining norm and length in a vector space, you can actually find that unit circle can be an ellipse. So we'll see what I mean. So in example 3, sketch the unit circle in R2 using the weighted Euclidean inner product, this function. Okay, this is a function that assigns to two vectors u and v this number. Okay, a unit vector is a vector where if you take the inner product of that vector with itself, you get 1. Okay, well, technically the norm of u is the square root of it, but the only way you could get the square root of is 1 is if the inner product is 1. Okay, but the normal vector u is the square root of the inner product of the vector with itself. Okay, so solution, if u is equal to x comma y, where x is the first component, y is the second component, because we're in R2. Vectors in R2 are two tuples, vectors with first components and second components. So u is an arbitrary vector in R2, meaning you can express it as x comma y, where x is the first component and y is the second component. Then the normal vector u is the square root of the inner product of u with itself. Now you're given that the inner product of u and v is this expression, where u1 and u2 are the components of u, and v1 and v2 are the components of v. But because you're taking the inner product of u itself, instead of v1 and v2, it's also u1 and u2. So the inner product of u with u and itself u is 1/9 u1 times u1 plus 1/4 times u2 times u2. Okay, but here the components are expressed as x and y, and so u1 is x and u2 is y. So this is 1/9 x squared plus 1/4 y squared. That's the inner product of u with itself. And then you take the square root of it. So it's the square root of 1/9 x squared plus 1/4 y squared. That's the norm of a vector u. Okay, and so keep in mind the unit circle is the set of all vectors u such that the norm of u is equal to 1. So if the norm of u can be expressed in this way, you want to find all the points x comma y such that this expression is equal to 1. So you want to find all the points x comma y such that the square root of 1/9 x squared plus 1/4 y squared is equal to 1. Or equivalently, if you square both sides, you have the same set of points x comma y that satisfy the equation 1/9 x squared plus 1/4 y squared equals 1. Okay, so you want to find all the points x comma y that satisfy the equation 1/9 x squared plus 1/4 y squared equals 1. Correspondingly, that's the set of points x comma y that lie on the unit circle. Okay, by defining our inner product space in this way, using the weighted Euclidean inner product with weights 1/9 and 1/4, we've also defined distance in our own way, right? When you have a different inner product function, you have a different distance, right? We define distance in terms of inner product. The distance between vectors u and v is the square root of the inner product of u minus v in itself. So if you have a different inner product function, that means you have a different distance function, okay? So distances, your notion of distance can fit right in with this definition. If you use an appropriate inner product space with an appropriate inner product function, then you can talk about distance the way you normally would think of it. But if you think more generally, where you have different inner product spaces with different inner product functions, then you could talk about other types of distance. Okay, so this distance is saying with a different distance, we now have a different shape of a circle, right? Normally, the distance of one away from a point would give you a circle, right? But now, because our distance is different, because our inner product is different, saying distance one away from a point no longer results in a geometric circle that we thought of. So here, it's expressed by this equation. And if you take, so you've taken calculus, and so hopefully you remember that this represents an ellipse. The general equation for an ellipse is of the form x squared over a squared plus y squared over b squared equals 1, right? Where a is the length of the, well, it depends which number is bigger. Okay, so here we found that we have x squared over 9 plus y squared over 4 equals 1. So that means a is equal to 3 and b is equal to 2 in order to match this equation with this one, right? The 9 is the a squared and the 4 is the b squared. So a is 3 and b is 2. And so if you were to graph, if you graph this ellipse, then the graph of that ellipse is just the ellipse centered at the origin, where you have 3 here and 2 there. So this ellipse, this is the set of all points x, y, so it's x squared plus over 9 plus y squared over 4 is equal to 1. And in that example, this is the unit circle. So the unit circle in this example is an ellipse. All the points x, comma, y that satisfy that equation are the points lying on that ellipse. If you take a point on this ellipse, x, comma, y, that's a point that would satisfy that equation, that would make it true. If you take a point not on that ellipse, x, comma, y, then that would be a choice of x and y that would not satisfy that equation. Okay? Okay, so new thought here. Let A be an invertible n by n matrix, and U and V be vectors in n space. Then the inner product of U and V, you can define this inner product as being AU dotted with AV. This equation 5 defines the inner product on Rn generated by A. So this is another inner product function. 5, this can also be expressed in this form. You could say the inner product of U and V is equal to AV transpose times AU. Or the same one could be expressed as the inner product of U and V is equal to V transpose times A transpose times AU. That's equation 6 of this section. Okay, but we're not going to spend much time on that. What's more important is a simpler one, which is in example 6. So if U is equal to capital U and V is equal to capital V are matrices in M sub nn. M sub nn is the vector space of n by n matrices with standard addition and standard scalar multiplication. Okay, so M sub nn would be normal n by n matrices, and when you add them, it would be the normal way you would add matrices. And then you took a scalar multiple of a matrix, it would be a normal scalar multiple of a matrix. Okay, so this set teamed with the operation of standard addition and standard scalar multiplication of a matrix. Those 3 things team up to be the vector space capital M sub nn, which satisfy all 10 axioms of a vector space. Okay, because you have those 3 things that satisfy the 10 axioms, it then means you can give it the name. You can give that team the name of vector space. You can then say you are a vector space. You satisfy the 10 axioms for a vector space. Okay, the team has been awarded the name vector space because they satisfy all 10 axioms of a vector space. Okay, so if you have U equals capital U, V equals capital V are matrices in that space. Remember, this is a vector space because it satisfies all 10 axioms. That means the matrices, right? A vector space is a set, an operation of addition, and an operation of scalar multiplication. That set in the team of 3 things, that set consists of objects, right? In this case, those objects are n by n matrices. Those objects in the set are what are called vectors. The team of 3 things is called a vector space. The objects in the set are called vectors of that vector space. Okay, so vectors in this vector space are n by n matrices. Okay, so a vector U is equal to a matrix capital U. The vector V is equal to a matrix capital V. This is just keeping with the standard notation that matrices are denoted by capital letters and that vectors are denoted by lowercase letters. Okay, so we have an intersection of notations. We have vectors that are represented by lowercase letters, matrices represented by capital case letters. And so when you're talking about a vector little u, you set equal to a matrix capital U, okay, to avoid confusion of notation. So if you take the inner product of U and V here, this is another inner product function on M sub nn, and it's defined as the trace of U transpose V. And this sounds very complicated, but when you actually calculate it, it's very easy. Let me show you why. So let's say you have these 2 matrices in M sub 2, 2. M sub 2, 2 is the vector space of 2 by 2 matrices with addition and scalar multiplication. So you have these 2 matrices. Now, if you do the inner product of U and V, it's equal to the trace of U transpose V. But if you calculate the trace of U transpose V, it's just equal to U1 V1 plus U2 V2 plus U3 V3 plus U4 V4. That sum of products is the trace of U transpose V. Okay? So even though the definition is weird, trace of U transpose V, calculating is very simple. You just take the corresponding components of matrices, multiply them, and then add the products. Okay? Also, the norm of U, you go strictly by the definition of norm of a vector. It's equal to the square root of the inner product of vector U itself. Well, the inner product of U with itself is the trace of U transpose U. But again, even though that's weird, the calculation of it is simple. Instead of saying U1 V1 plus U2 V2 plus U3 V3 plus U4 V4, instead of these being these, they're the same numbers as these. So this is U1, this is U2, this is U3, and this is U4. So if U1 times U1 plus U2 times U2 plus U3 times U3 plus U4 times U4. That's U1 squared plus U2 squared plus U3 squared plus U4 squared. That's the trace of U transpose U. That's the inner product of U with itself, where little u is the matrix capital U, which is in a vector in capital M sub 2, 2, the vector space of 2 by 2 matrices. Okay. For short, mathematicians will not, when a mathematician is referring to a vector space, they will not refer to it as all three things in the team. For short, they'll talk about the set as being the vector space. What they really mean is the team of three things that make up the vector space. Okay. So if you had a vector space B, which consisted of a set B, an operation of addition, an operation of scale multiplication, technically a vector space is the team of three things. But a mathematician wants to be lazy and not say all three things every time he's talking about it. So instead, he'll say vector space B, where B is the set, meaning the vector space of three things. Okay, so oftentimes the language will be shortened. And so in a sense, what you say doesn't make sense, but it does because you know what you really mean when you say something. Okay. So when a mathematician speaks, they don't mean the thing they say, they mean something else, but they're just saying something for short instead of what they, okay? It's a little confusing. Example 7. If P is equal to A naught plus A1x plus A2x squared plus dot 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 plus A n xn, and Q is equal to B naught plus B1x plus B2x squared plus dot 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 plus Bn xn. So that means P and Q are each polynomials of degree n, at most n, I should say, because an could be 0. If an is 0, then the highest degree with a non-zero coefficient could be less than n. But P and Q are polynomials of degree at most n. They're elements of the vector space P sub n. P sub n is the vector space of at most n degree polynomials. Okay, so then 9 below defines the standard inner product of Pn. So the inner product of P and Q polynomials is equal to sum of these products, where they're the corresponding the coefficients, you multiply corresponding coefficients, A naught B naught plus A1 B1 plus A2 B2 plus dot 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 plus A and Bn. That product is the inner product of polynomials P and Q for the standard inner product on Pn. Okay, you can have different inner product functions for Pn, but this function is important, and so it's given, it's a special one, and so it's given the special name, the standard inner product of Pn. Okay, so the norm of P is equal to the square root of the inner product of P itself, which is the square root of the sum of the squares of the coefficients of the polynomial P. So the square root of A naught squared plus A1 squared plus A2 squared plus dot 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 plus An squared. This is the norm of the polynomial P relative to this inner product, right? If you change the inner product, then you're changing the norm of the same polynomial. Note, if you change it, okay, that's what I just said. Okay. Example 8. If P, which equals P of x, is equal to this polynomial, and Q is equal to that polynomial, or polynomials in Pn, and x naught to xn are distinct real numbers, then you can define another inner product function on Pn called the evaluation inner product at x naught coming to xn. And so the inner product of PQ for this function is defined as P of x naught times Q of x naught plus P of x1 times Q of x1 plus dot 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 plus P of xn times Q of xn. It's just another function that defines another inner product space on the same set of polynomials. Okay? And so here in this different inner product space, because it's a different function, the norm is now different. The norm of P is still the square root of the inner product of P with itself, but now the inner product of P with itself is a different value. It's the sum of squares of these things. Instead of it being this, it's now this. Okay, and so you have a different norm for the same polynomial P. And in this case, it's the norm of this polynomial P relative to the evaluation inner product at x naught to xn. Theorem 6.1.2. If U, V, and W are vectors in a real inner product space V in case of scalar, then you have these 5 properties. Okay, where if there's a 0 somewhere there, the inner product is 0. You can separate this and you get the sum of these two things. If you have a minus sign here, you subtract the 2. If you have a minus sign here, you subtract the 2. And if you have a scalar outside of it, you can move it to the second one here. Okay. So these are 5 properties of interproduct as a theorem. Okay, so that's the end of 6.1. So next is 6.2 on angle and orthogonality in interproduct spaces. Okay, so theta is the angle between vectors u and v. Theta is equal to cosine inverse of u dot v divided by the norm of u times norm of v. What that means is that because cosine inverse, the domain of cosine inverse is only from -1 to 1 inclusive. That means that when you plug into the cosine inverse function, u dot v divided by the norm of v times norm of v, that thing can only be between -1 and 1 inclusive. Okay, theorem 6.2.1, Cauchy-Schwarz inequality. If u and v are vectors in a real interproduct space V, then the absolute value of the interproduct of u and v is less or equal to the norm of u times norm of v. Okay, this is a very important theorem. It's called the Cauchy-Schwarz inequality. Okay, some notes. If you take the interproduct of u and v and you square it, it's less or equal to the interproduct of u with itself times the interproduct of v with itself. If you square both sides, you get the interproduct of u and v squared is less or equal to, if you square this interproduct, you get the norm of u squared. If you square this interproduct, you get the norm of v squared, as you get this inequality. That's squaring both sides of that. So these are both non-negative numbers. So when you square both sides, it doesn't change the direction of the inequality. Now, if you take cosine of theta, it's equal to this quantity, and theta is between 0 and pi inclusive. Okay, so theta is equal to cosine inverse of that. It's the angle theta between vectors u and v. Okay, here's an example where we compute cosine theta. Let's say u is equal to the matrix u and v is equal to the matrix v. Solution is the interproduct of u and v is equal to 16 because if you take the square root of 1, if you take 1 times -1 plus 2 times 0 plus 3 times 3 plus 4 times 2, you get 16. Okay. Okay, so then that's that. And then the norm of u is just taking the square root of the sum of the squares of the entry. So it's the square root of 1 squared plus 2 squared plus 3 squared plus 4 squared. That's the square root of 30. Okay. And the norm of v, the norm of this matrix V, is the square root of the sum of the squares of the entries of matrix V. So it's the square root of -1 squared plus 0 squared plus 3 squared plus 2 squared. That's 1 plus 0 plus 9 plus 4. And that's the square root of 14. So cosine of theta, using our formula, cosine of theta is the interproduct of u and v divided by the norm of u times norm of v. So I did these calculations just to plug in. So in the numerator, you plug in 16. In the denominator, you plug in the square root of 30 times the square root of 14. If you do 16 divided by that, you get approximately 0.78. Okay, theorem 6.2.2. If u, v, w are in a real interproduct space V and k is any scalar, then the norm of u plus v is less or equal to the norm of u plus norm of v. This is from the triangle inequality. And if you take the distance between u and v, it's less or equal to the distance between u and w plus the distance between w and v. So very quickly, I'm going to show you what that is. If you take two vectors, u and v, take u plus v, so you have a vector u and a vector v. This is vector u and a vector v. And so the vector, this vector is u plus v. And so remember with triangles that if you take the norm, if you take the length of the hypotenuse, it's less or equal to the sum of the lengths of the sides. And so that means that the length of u plus v, the length of the hypotenuse of that triangle is less or equal to the sum of the lengths of the legs of the triangle, less or equal to the length of u plus the length of v. And so that's the triangle inequality for vectors. The norm of u plus v is less or equal to the norm of u plus norm of v. And the distance works exactly the same way. Okay. Definition 1. Two vectors u and v in an interproduct space capital V is called orthogonal if their interproduct is equal to 0. Okay. So orthogonal vectors are vectors whose interproduct is equal to 0. Okay, that's the meaning of orthogonal vectors. Theorem 6.2.3. Generalized theorem of Pythagoras. If u and v are orthogonal vectors in a real interproduct space, meaning their interproduct is 0, then this equation holds. Definition 2. If w is a subspace of a real interproduct space V, then the set of all vectors in V that are orthogonal to every vector in W is called the orthogonal complement of W. And it's denoted by W perp, this symbol. Okay, an illustration of that would be if you have a vector space, let's say in R3. So in R3, you have 3 axes. You have the X, Y, and Z axis, maybe, if you call them that. Right? That's the origin. Okay, remember vector spaces in R3. One possibility is that you have a plane through the origin. So if you have a plane through the origin, it contains the origin, right? This plane, and you want to talk about its orthogonal complement. This is a vector space in R3. If you want to talk about its orthogonal complement, you want to talk about all the vectors that are perpendicular to every vector in that plane. And so that space is the line that's perpendicular to that plane. Okay? The dot is not part of the line. Maybe we'll just delete the dot. It's perpendicular to the plane. And so if you take any point on this line, that point corresponds to a vector from the origin to that point. That vector is perpendicular to every vector on the plane. So if I take any point in the plane, take the vector from the origin to that point, that vector is perpendicular to that orange one. If I take another vector on the plane, it's still perpendicular to the same vector on that line. To every single vector on this plane, which corresponds to points on the plane, all of those vectors, all those infinitely many vectors are orthogonal to that one orange vector on the purple line. But every point on that line corresponds with an orange vector, which is perpendicular to every vector on the blue plane. So this purple line is the orthogonal complement of that plane. So if the W is the plane W is a subspace of R3, then that line perpendicular to W is W perp, the orthogonal complement of the plane, or subspace W of R3. Okay? Okay. Theorem 6.2.4. If W is a subspace of a real and approximate space V, then W perp is a subspace of V. So if you take the orthogonal complement of a real and approximate space, then it's also a sub. If W is a subspace of a real and approximate space V, then its orthogonal complement W perp is a subspace of V also. Also, if you take the intersection of a subspace with its orthogonal complement, it's exactly equal to the zero set. Okay, Theorem 6.2.5. If W is a subspace of a real finite dimensional interproduct space V, then the orthogonal complement of W perp is W, meaning if you take W perp perp, it's equal to W. Okay, we start with the subspace W and think of its orthogonal complement. Then if you take the orthogonal complement of the orthogonal complement, you get back the original subspace W. Okay, in the picture I drew, the original subspace was W, and W perp, the line, was its orthogonal complement. If I take the orthogonal complement of W perp, that line, if I take the orthogonal complement of that pink line, I get the plane W, or the original subspace W. Okay, so W perp perp is equal to W. Okay, so example 6, let W be the subspace of R6 spanned by these four vectors. Okay, so the span of four vectors is the set space of all linear combinations of those four vectors. Okay, so the span, so that's the space spanned by these four vectors. Find a basis for the orthogonal complement of W. Find a basis for the orthogonal complement of the span of those four vectors. The span of a set of vectors is a vector space. Okay, solution. Take A, this matrix A, where the rows are made from these four vectors, W1, W2, W3, and W4. Those consist of the rows of that matrix A. We want to find a basis for the orthogonal complement of W. Since the row space and null space are orthogonal complements, right? If you take the row space of the matrix and the null space, they are orthogonal complements. And so the row space of this matrix is the span of the rows of the matrix. The span of the rows of the matrix is the same as the span of the four vectors, because the rows of the matrix are the four vectors there. Okay, so equivalently, the row space of this matrix is the span of those four vectors. Row space is the span of the rows. Okay, so the null space is the orthogonal complement of the row space. And so we chose our rows appropriately, so that way the null space is the orthogonal complement of W. So this problem boils down to finding the null space of this matrix A. And so these three vectors form a basis for the null space. And so these three vectors form a basis for the orthogonal complement of W. Okay. Okay. Remember, the null space is the set of all vectors x such that ax equals 0. Okay. And so by finding all those vectors, finding a basis for that space, you're finding a basis for the orthogonal complement of W. Okay, 6.3. This is the last section for today. It's called the Gram-Schmidt process, or QR decomposition. So again, I'm going to extend this class so that we'll still have a review for the second exam. Okay. And if you have to go or you're getting tired, I will record it. And so it'll be on YouTube and you'll be able to watch it either later tonight or tomorrow or again, how many times you want for the exam. Okay. So we are recording. I will stay longer. Okay. So 6.3 is on the Gram-Schmidt process QR decomposition. Definition 1. A set of two or more vectors in a real inner product space is said to be orthogonal if all pairs of distinct vectors in the set are orthogonal. An orthogonal set in which each vector has norm 1 is said to be orthonormal. Okay, so if you have a set of vectors where if you take any pair of them, they're orthogonal, it's called an orthogonal set. Two vectors, again, are orthogonal if their inner product is 0. So an orthogonal set is a set where any pair of vectors, their inner product is 0. And further, you can take an orthogonal set, and if the norm of all the vectors are 1, the length of every vector in that orthogonal set is 1, you have an orthonormal set. There's additional structure on orthogonal set. Example 1, let V1 equal to this vector, V2 equal to this vector, and V3 equal to that vector. And assume that R3 has the Euclidean inner product. Saying that R3 has the Euclidean inner product means that you're saying your inner product function is the standard inner product function. That's when you take the components, multiply corresponding components, and then add the products to get the Euclidean inner product of two vectors. So the Euclidean inner product of V1 and V2 would be 0 times 1 plus 1 times 0 plus 0 times 1. You're multiplying corresponding components of the vector and then adding the products. Okay, so then S is equal to the set of these three vectors is orthogonal, because if you take the inner product of V1 and V2 and the inner product of V1 and V3 and the inner product of V2 and V3, all three of them are equal to 0. And if you switch the order, the inner product is what's called commutative. You can switch the order of the vectors and it doesn't change the value. So the fact that the inner product of V1 and V2 is 0 means the inner product of V2 and V1 is also 0. Okay, so because these three inner products are 0, corresponding to these three other inner products are also 0, which means all 6 possible inner products of these three vectors are 0, which means that it is an orthogonal set, the set V1, V2, V3. The process of multiplying a vector V by the reciprocal of its length to get a unit vector in the same direction as V is called normalizing V. Okay, what that means is if you have a general vector V, right, you want to think of the unit vector in the same direction as V. So if this is a vector V, you want to talk about the unit vector in the same direction as V. So let's say this is the unit vector of V. So this length is length 1. Okay, it's just a vector in the same direction as V, but length 1. So every vector has a corresponding unit vector. Okay, this is called normalizing V. You take a vector V and multiply it by the reciprocal of its length. Okay, so for instance, if you had this vector V, right, and the norm of V was equal to 5, then if the norm of V was equal to 5, then multiplying it by 1/5 would mean that you changed the length from 5 to 1. But by multiplying it by a positive number, you didn't change its direction. So 1/5, so U here is equal to 1/5 V. Okay, so if you have a vector V in a certain direction and it has a length, just divide it by its length, and you end up same direction, just length 1. Given an orthogonal set, to get it to be orthonormal, just multiply each vector by the reciprocal of its length to form an orthonormal set. What that means is if you have an orthogonal set, that means each pair of vectors are orthogonal, right? Or orthonormal means also the norm of every vector is 1. So the only additional thing you need is that the lengths have to be 1. If they're not already 1, you could just multiply each vector by the reciprocal of its length to make them 1. Okay, if you rescale a vector, right? If you make a vector shorter or longer, but it's in the same direction, it doesn't change whether or not that vector is perpendicular to another vector. Okay, so if you just change the length of the vector but keep its direction the same, then it's still either orthogonal or not orthogonal to any other vector. Okay, so if you have already an orthogonal set, by changing the length of each of the vectors, you're not changing whether or not it's orthogonal. So if you're given an orthogonal set, all you have to do is divide each vector by its length to make them length 1 vectors, and you still have an orthogonal set. But now the new vectors are also length 1. And so you form an orthonormal set from the orthogonal set now. Okay, example 2, normalize this vector V3, which is 1, 0, -1. So the norm of V is equal to the square root of the sum of the squares of the components of that vector. So it's the square root of 1 squared plus 0 squared plus negative 1 squared. That's the square root of 2. So norm of V3 is equal to the square root of 2. U3 is equal to, so U3 is normalizing vector V3. U3 is the vector in the same direction as V3 but length 1. So to do that, you just take the vector V3 and divide it by its length. So that's the vector V3 divided by its length, which is the square root of 2. And so you're dividing each component by the square root of 2. So this is 1 over the square root of 2, comma 0, comma negative 1 over the square root of 2. So this vector is in the same direction as V3, but only length 1 now. Okay, remember, so if you change the length to length 1, it doesn't mean it's necessarily shorter. If your original length was 1/5, then you made it length 1, you would actually be making the vector larger, longer in length, right? So normalizing a vector doesn't always mean making the vector shorter. It means you're changing its length to 1. And so if the length was less than 1, it could become actually a longer vector. So theorem 6.3.1. If S is equal to this set of vectors V1 to Vn is an orthogonal set of non-zero vectors in an interproduct space, then S is linearly independent. Okay, so if you have a set of vectors that, if you have an orthogonal set and they're non-zero vectors in an interproduct space, then your set is linearly independent. Okay, so if you have a collection of vectors that are perpendicular to each other and they're non-zero, then they have to be linearly independent. Okay, in an interproduct space, a basis consisting of orthonormal vectors is called an orthonormal basis, and a basis consisting of orthogonal vectors is called an orthogonal basis. Okay, so you have bases, but now if in addition you have a basis where the basis vectors are orthonormal vectors, it's called orthonormal basis. If you have a basis consisting of vectors that are orthogonal, then it's an orthogonal basis. Okay, it's just certain types of bases. Okay, so here we're going to use that idea. So in theorem 6.3.2, if S is this set of vectors V1 to Vn is an orthogonal basis for an interproduct space V, and if U is any vector in V, then U can be expressed in this way. Okay, it's an expression of U in these terms, but you have to be given an orthogonal basis already. V1, V2 to Vn form an orthogonal basis, and now you're expressing U as a linear combination of those vectors, where the coefficients are given by these expressions. B, if S is equal to this set is an orthonormal basis for an interproduct space V, then, and if U is any vector in the vector space of capital V, then U can be expressed in this way, where it's still a linear, it's still a linear combination of V1 to Vn, except the coefficients now you only use the numerators. And the reason for that is because you have an orthonormal basis. The norms of each of these vectors is 1. And so in your original expression, you're dividing each of them by the norms of the vectors squared. But if the norm of every vector is 1, you're dividing each of these fractions have 1 squared in the denominator. And so if you're given a further structure of an orthonormal basis, you don't need the denominator of 1 squared here. And so you can just write it like that. So given S is an orthogonal basis, then in A, we represented U as a linear combination of V1 to Vn in this way. Well, if you want the coordinates of U relative to this basis S, then the coordinates of U relative to S are just the corresponding coefficients of V1 to Vn. So these components of this vector correspond with the coefficients from V1 to Vn. If S is an orthonormal basis, we've expressed U as a linear combination of V1 to Vn in this way, where the coefficients of V1 to Vn correspond with these inner products. Then these inner products make up the components of the coordinate of U relative to this base orthonormal basis S. So see how these coefficients correspond with the components of this vector. This is how you get the components of a vector relative to a basis. You write that vector as a linear combination of the basis vectors, and then the coefficients of those basis vectors correspond with the coordinates of that point relative to that basis. Example 5. So I'm going to extend class further and I'm going to give a review. I will stay as long as you want. And if you can't stay, or if you want to watch it later, the video will be online. If you have questions, please stay and ask them. So let V1 equal this vector, V2 equal this one, and V3 equal that one. S is equal to this set is an orthonormal basis for R3 with the Euclidean inner product. Express U as a linear combination of, I'm almost done, of the vector S in capital S and find the coordinates of U relative to S. So the inner product of U with V1 is 1. The inner product of U and V2 is -1/5, and the inner product of U and V3 is 7/5. Okay, for this is easier than other things, but if you take the inner product of U with each of these vectors, you get these numbers, right? You're just multiplying the components of U with the corresponding components of these vectors, adding up the products and getting a number. So that's how you compute these three inner products, okay? Now, because you have an orthonormal basis, you look at this. Given an orthonormal basis, you can write U in this form. So when you're learning this, just strictly by the notes, you have an orthonormal basis. So by B, you have this expression. So U is equal to this expression. Then you plug in. What are the values of these three inner products? You plug those numbers in there, 1, -1/5, 7/5. So these three inner products have those three corresponding values. I've now expressed U as a linear combination of V1, V2, and V3. Now, so that means the coordinates of U relative to this basis S is equal to the 3-tuple, where the components correspond with the coefficients of V1, V2, and V3, respectively. 1, -1/5, 7/5. Okay, so when you're studying, I definitely think you should look at this section because I think this illustrates well how you get the coordinates of a vector relative to a basis and how this theorem works. Okay, I think you can see it well. It's just a lot of stuff. If you look at this slower, I think if you look at this, you can see it kind of easily. Okay, theorem 6.3.3, projection theorem. If W is a finite dimensional subspace of an inner product space V, then every vector U and V can be expressed in exactly one way as this sum, where W1 is in the subspace W and W2 is in the orthogonal complement of W. So that means that you're expressing U as a sum of a vector in the subspace plus a vector in the orthogonal complement of that subspace. So if you fix a subspace that's finite dimensional, then you can express any vector U as a vector in that subspace plus a vector in the orthogonal complement of that subspace. Okay, if you're looking at this previous picture, right, where I have the subspace W as a plane and W perp is the line perpendicular to that plane. If I take any vector in R3, I can think of it as a sum of a vector in the plane W plus a vector in W perp. Okay, since they're perpendicular to each other, then I can go some way along the plane W and then some way along the perpendicular line W perp, and I'll end up at any point I want on R3. Okay, that's what that's saying. Okay, there's exactly one way to do that. Okay, so W1 is the projection of U onto W. Okay, so W1 is the projection of your vector U on the subspace W. W2 is the projection of U on the orthogonal complement of W. Okay, so this is the W1 and W2 in Formula 8, and I'm calling this Formula 9. W1 is the orthogonal projection of U on W. U2 is the orthogonal projection of U on W perp. Okay, so that's how the notation, and I'm writing on words so you see how the notation works. U is the sum of those two. U is the projection of U into W plus U minus projection of U into W. This is an obvious statement, but important to note. Okay, all very close to being done with the material for today. Theorem 6.3.5. Every non-zero finite dimensional inner product space has an orthonormal basis, the Gram-Schmidt process. To convert a basis to an orthogonal basis, perform the following computation. So you start with the basis U1 to UR, and you want to convert it to an orthogonal basis V1 to VR. Do the following. I want to create vectors V1 to VR. That's an orthogonal basis, given vectors U1 to UR that form a basis. Okay, so I want to create the vectors V1 to VR. I don't have them. I do start with the vectors U1 to UR that form a basis. Step one is let V1 equal to the first basis vector U1. So it's very simple. Your first new basis vector V1 is going to be the same as your first old basis vector U1. Step two, your second new basis vector V2 is going to be equal to the old basis vector U2 minus this, minus the inner product of U2 with V1 divided by the norm V1 squared times V1. This is a weird thing to remember, but if you notice, all these terms are very much like this one. So if you remember this one expression, you can remember everything else from it. Step three, the third new vector is equal to the third old one minus this expression minus that one. This is a V2. Okay, so here, notice how there's a V1 throughout, and notice here there's a V2 throughout, right? And so we're forming V3 using U3 and using V1 and V2. So every time you have another new basis vector, you're using the other new basis vectors prior to it to construct the next new one. So to construct V3, you're using V1 and V2. So when you say V3 equals U3 minus 2 terms, it's minus 2 terms because you've already made 2 terms. If you're constructing V4, there's going to be U4 minus 3 terms, where each of those 3 terms correspond with the 3 vectors you already formed before V4. Make sense? If you were making V10, it would be U10 minus 9 terms, where the 9 terms were from the previous 9 vectors V1 to V9 you made before V10. Does that make sense? I will not ask you to construct V10, okay? I'm just giving it as an extreme example of how this works, right? So you take when you have U2 here, this is the U2 here, and then it's just V1 throughout. Here you have U3, so you have U3 here, and then there's V1s, and here's a U3, you have V2s throughout. See the pattern? So you just follow that pattern, and you have expressions for all your V's. If you want to convert, if you have a basis with, let's say, 5 vectors, you would want a new basis with also 5 vectors. So the number of steps is determined by the number of vectors in your original basis. If you had 2 vectors in your original basis, you would have 2 vectors in your new basis until you stop at step 2. So after you do step 3, or maybe not even step 2, you continue for R steps, where R is the number of basis vectors you started with. So you want to do this process exactly R times, which corresponds to the number of vectors you had in your original basis. Okay? So then afterwards, these vectors you get V1 to VR form a new basis, which is orthogonal. These vectors you're creating, V1 to VR, are now basis vectors for the same vector space. It's still a basis, but now this basis is orthogonal. If you take any 2 of these V's that you made and take their inner product, you'll get 0. Further, if you take this orthogonal basis you formed from V1 to VR and you want an orthonormal basis, you want a basis consisting of vectors that are not just orthogonal to each other, but also have norm 1, then all you have to do is normalize each of these vectors you created from V1 to VR, meaning you take each of those V's and divide them by their lengths, making them into length 1 vectors in the same direction. And by scaling a vector, you don't change its orthogonality with other vectors. And so when you have an orthogonal set and you multiply each vector by 1 over its length, you're getting a new set of vectors whose lengths are 1, but it's still orthogonal. Okay, doesn't change that as long as you do it correctly. Theorem. This is the last thing I'm going to say in the lesson. If W is a finite dimensional inner product space, then every orthogonal set of non-zero vectors in W can be enlarged to an orthonormal basis for W. Okay, meaning if you have an orthogonal set of non-zero vectors, you can enlarge that set, add more vectors into it to create an orthonormal basis for W. And B, every orthonormal set in W can be enlarged to an orthonormal basis. This should be orthogonal, sorry. It's every set of orthogonal non-zero can be enlarged to an orthogonal basis for W. Every orthonormal set in W can be enlarged to an orthonormal basis for W. Okay, that's the material. Now the homework is not due next class because the exam is next class. This homework is due December 7th. Okay, these are the chapter 5 and 6 problems in the review sheet. Okay, that is due next class. Okay, so these problems. Okay, these are due December 7th. Okay, we are almost done with the material. Though there's a bunch of problems here, this is actually not that much. We're almost done with all the material in the course. Okay, this is the homework for December 7th. There's no homework for next class because the exam is next class. Okay. Okay, so now I'm going to stay. I just ended on time 9:50, but I'm staying because we're going to have a review. Okay, so now there's a review for test 2. And so in the review, I guess you just want me to go over the review. You want me to go over maybe the practice test or something? Does anyone have specific problems they want me to go over, or do you want me to just run through the practice test? Okay, so I heard practice test, yes, let me just go. So this is the practice test for test 2. I'm going to run through it, okay? I'll try and do it quickly because it's already 9:50. So number 1, you want to write that vector V as a linear combination of those vectors, okay? Okay, what I'm going to do is, if I take a picture of the screen, I don't have to go back and forth. Okay, so in your homes, I would suggest is that you have the test in front of you. Okay. Okay, so have the test in front of you. and I will go. Okay. Okay. Where are we? Here. Okay. So for number one, we want to write that vector b as linear combination of those vectors. Okay, so actually, we'll go to the whiteboard. Whiteboard will be faster. Okay. Um, if if you need me to write clear, just say, no, we'll write clear. Okay. That is the vector 5, 3, 0, and you want to write it as a linear combination of those vectors. So I'm going to make those coefficients C1, C2, C3, and C4. So C1, 2, 0, 1 plus C2 times 1, 4, 3 plus C3 times the vector 8, 1, 1 plus C4 times the vector negative 4, 6, 1. Okay, so I just want to express that vector as a linear combination of those 4 vectors. And so what you want to do is just add up those multiples, scalar multiples. So if you do that, the first component becomes 2C1 plus C2 plus 8C3 minus 4C4. The second component becomes 4C2. I'm going to write it here so it lines up. 4C2 plus C3 plus 6C4 and then the third component is C1 plus 2C plus 3C2 plus 3C2 plus C3 plus C4. Okay, so I now have that matrix is equal to 5, 3, 0. So that means you just want to set each corresponding component equal to each other. So I want to set 5 equal to this. I want to set 3 equal to this, and set the 0 equal to that. Okay, and so then that I'll have 3 corresponding equations. Okay, I guess I'm going to write this out. So, okay, good. Okay, you can see that on the screen, I think still. Okay, and then when we get to reduced row echelon form. Okay, so now 2, 1, 8, negative 4, 0, 4, 1, 6, 1, 3, 1, 1, and then 5, 3, 0. Okay, so we want to get this to reduce row echelon form. So I'm going to multiply the first row by 1/2. So you get 1, 1/2, 4, negative 2. And then this is 5/2. Right by hands. Okay, then this I'm going to multiply this row by 1/4. Well, yeah, okay, I'm going to multiply by 1/4. So this is 1, 1/4, 6/4, which is 3/2, and then 3/4 here. And then I'm going to multiply, and then what I want to do is I'm going to add the negative 1 times this new first row to the last row there. And so I'm going to cancel out the 0 there. So I hope that makes sense. So then this is 2.5, this is 5/2. And then I'm going to take, so it's negative 3. And then I'm going to take 3. And then I'm going to take negative 5/2. So the point is just, I'm getting it to reduce row echelon form. Okay, so all of these individual things took time to explain, and certainly can't explain in detail as much as I did originally, right? So I have to gloss over some of the earlier steps we've done before. Okay, so I'm going to try to quickly get this to reduce row echelon form. Okay, so in the last row, I'm going to multiply by 2/5. So this is 0, 1, negative 6/5. Okay, I'm multiplying by 2/5. That's 6/5. Multiplying by 2/5. This is negative 1. Okay, and then This is also 0, 1, 1/4, 3/2, 3/4. So the goal is just to get this to reduced echelon form, and then you'll have your coefficients. So, and there'll be infinitely many coefficients you can choose from. It's going to be large selection choices for answers. -2 for this problem. It's a positive 5/2. So you have this row. Okay, I'm going to take -1 times that row and add to the other. So I get 0, 0, -1/4, -1/4, -24. I don't know, wait, yeah, -24, minus 29/5. Okay. Okay, and so the -3/2 plus 6/5, it's 12, minus 3/15. Minus 7/4. Okay, so now in the last row, you have 0, 0. I'm going to multiply the last row by -5/29. -5/29, 35/116. Give me 1 second. Let me just. Okay, so all right. I'm going to say -1/4. Okay, I guess I didn't make a mistake up to this point. Okay, so then you have -1/4. The test problem will not be this long. Okay, so hold on 1 second. Second. let's just go back to number one because I'm making some kind of calculation error with it and I'm not seeing it. I'll go back to number one. Okay, number two, find the distance between the given parallel planes. Okay, so you have two planes and you just want to find the distance between them. Okay. Okay, so for D, let's go to the whiteboard. Okay, so when you have the distance, D, right? So you have the absolute value of your two equations are 2x plus y plus 2z is equal to 8, and 4x plus 2y plus 4z is equal to -5. Plus 5 equals 0. Okay, so here you just take, okay, so let's look at one equation, this one. A solution would be of the form 2, 0, 2. So that would solve that equation. If x was 2, y was 0, and z was 2, you have 4 plus 0 plus 4 is 8. So 2 comma 0 comma 2 is a solution to the first equation. And so now what you do is you just take the other equation, 4, and then plug in the corresponding values for x, y, and z. So you have 4 times 2 plus 2 times 0 plus just wait, something like that, plus 2 times 0 plus 4 times 2. I use the dark blue. So use the dark blue. Okay, 4 times 2 times 0 plus 4 times 2. And so then you have plus 5. And you divide it by the square root of the sum of the squares of that equation. So you have 4 squared plus 2 squared plus 4 squared. And so now the numerator becomes the absolute value of 8 plus 0 plus 8 plus 5. So that's the absolute value of 21 in the numerator. And in the denominator, you have the square root of 16 plus 4 plus 16, which is the square root of 36. So this is equal to 21 over 6. So the distance between those two planes is 21 over 6. Okay? So you just take your two equations, you want the distance between them, and you can choose any one you want. So I chose 202 just because for me that was the easiest one. You could have chosen 400. That also would work. Any solution you want for one equation, you would then plug into the other one, take the absolute value of the expression on the left side. You want to make sure your expression is an expression equaling to 0, and then you plug in the solution into that expression, take the absolute value in the numerator. The denominator is the sum of the squares of the coefficients of those terms. So you have this 4 here, you have this 2 here, and you have this 4 here, not the constant term. And you take the squares of those coefficients of that expression. The 5 doesn't factor in the denominator. Okay, and so then you get the distance between those two planes. So this is number 2 in the review. Okay, we keep going. Okay, so now 3, find bases for the null space and row space of A. Okay, I could do that. Let's do the faster ones first. Some of them by a lot of computations. So here, 5 is a faster one. 5, find that one's done. Okay, find 2. Looking at this one, find 2 unit vectors orthogonal to both U and V. Okay, so so if you take the cross product of 2 vectors, if you take U cross V, then the result is a vector that's orthogonal to both U and V. Okay, so okay, so for number 5 on the view exam, if you have U cross V, then you take the determinant where the first row are the components of U, and I mean the second row, the first row below IJK, and then this bottom row is the components of V. So that's the components of U and V respectively, right? U is the vector 1, -1, 1. V is the vector 0, 4, 4. So what I'm thinking of is the fact that if you take U cross V is a vector that is orthogonal to both U and V. So when you find U cross V here, you're finding a vector that is orthogonal to both U and V. Okay, so this is equal to I times the determinant of the submatrix -1, 1, 4, 4 minus J times the corresponding submatrix, which is 1, 1, 0, 4 plus K times the determinant of the corresponding submatrix is 1, -1, 0, 4. And so now this is equal to I times, this is -4 minus 4, which is -8, minus J times that, which is 4 minus 0, which is 4, plus K times that determinant, which is 4 minus 0, which is 4. So this is equal to the vector -8, comma, -4, comma, 4. So U cross V is -8, comma, -4, comma, 4. So this is a vector orthogonal to both U and V. The problem is find 2 unit vectors orthogonal to those 2 vectors U and V. So I want 2 unit vectors orthogonal to them. So far, I found a vector orthogonal to U and V. I want 2 unit vectors orthogonal. So what I'm going to do is I'm going to find the norm of this vector. So the norm of that vector U cross V is equal to the norm of the vector -8, comma, -4, comma, 4. That's equal to the square root of the sum of the squares of the components of that vector. So it's the square root of -8 squared plus -4 squared plus 4 squared. This is the square root of 64 plus 16 plus 16. So this is equal to the square root of 96. Okay, and so then the square root of 96, so 48, 24, 48, 24, 12, 6. Okay, so this is the square root of 16 times the square root of 6, which is 4 root 16. Okay, so the norm of U cross V is 4 root 16. And so now if I take this vector U cross V and divide it by its length, I'm normalizing the vector, I'm finding a unit vector in the same direction. That vector will still be orthogonal to both U and V. So if I take the vector -8, comma, -4, comma, 4, and divide it by its length, 4 root 6, the result is -2 over root 6, comma, -1 over root 6, comma 1 over root 6. So I just took the vector -8, -4, 4 divided by its length 4 root 6, and I get -2 over root 6, comma -1 over root 6, comma 1 over root 6. So then that is a unit vector orthogonal to both u and v. So if I already have a unit vector that's orthogonal to u and v, all I have to do is take the negative of it, just go in the opposite direction. If you have a unit vector and you go in the opposite direction, it's still a unit vector. If you have a vector orthogonal to two other vectors and you just take its opposite, it's still orthogonal. And so I can also, this is one answer. This is one vector orthogonal to both u and v, because it's just u cross v divided by the norm of u cross v. And then a second one, this is one of them. The second one is just the negative of that vector, which is the vector 2 over root 6, comma 1 over root 6, comma -1 over root 6. Okay, and so those are two unit vectors that are orthogonal to both u and v. If you want, you could test it. It's an exam, so if you have time, you could test it. You could take the norm of both those vectors, and you get that both of those norms are 1. You could take you could take the inner product of each of those vectors with both u and v, and you'll get 0 both, but all the zeros each time. And so you could check if you want to, but that's the answer. So this procedure, the procedure works, and so that's enough to know that you have two vectors orthogonal to both u and v that are both of norm 1. Okay. Oh, wrong place. Okay, so that's number 5. And so now I've done number 5. Okay. So I'm going to do the faster ones first. So now in 4, we want to use matrix multiplication to find the image of the non-zero vector -5, 12 when it is rotated about the origin through an angle of theta equals -60 degrees. Okay, so there's the standard matrix for rotating about the origin. Okay, so yeah. Okay, so you just have the standard matrix. Yeah, okay, that's exactly what that is. Okay, good. Okay, so then I want to make sure everything's perfect. Okay, now this is 4. Okay, so the standard matrix for rotation about the origin by an angle of by an angle of theta is the matrix cosine theta, sine theta, negative sine theta, cosine theta. Okay, this is the standard matrix. This is the standard matrix for rotation about the origin by an angle of theta. Okay, so the transformation of rotating about the origin by an angle of theta is given by the standard matrix. This is the standard matrix. So in the problem, they want you to rotate the vector -5, 12, where an angle of theta, which is -60 degrees. Okay, so if you start with the vector -5, 12, right? X is -5, y is 12, and you want to rotate it by -60 degrees, meaning you're going to rotate it clockwise by 60 degrees, right? So if you were rotating by a positive amount, like +30 degrees, you'd be going counterclockwise, right? But if you're rotating by negative 60 degrees, you'd be going this direction, right? So negative 60 degrees is going 6 degrees in the opposite direction. Does that make sense? So I want to rotate this vector by that amount. So instead of drawing just those, I'm going to write out the vector, the exact vector that we're dealing with. So down here. So you have the vector negative 5, 12. So the vector negative 5, 12. And want to rotate it by 60 degrees about the origin. Okay, so this vector has a certain angle with respect to the x-axis, right? This is the angle. Now I want to rotate it by negative 60. So so then that the result is just, right, if you're on the circle centered at the origin with that point through it, you just want to move along that circle by an angle of 60 degrees, right? So you'll end up at another point on that same circle where the angle between them is 60 degrees, but the 60 degrees is going in this direction. It's going clockwise because we're rotating by negative 60 degree rotation, right? A negative 60 degree rotation would be 60 degrees in the clockwise direction. That makes sense? Okay, so we're gonna end up at a new point, and the goal is to find what this new point is. What is that? Okay, we want to find what that new point is. So it's an angle of negative 60. So you just plug in negative 60 degrees into this matrix. Okay. It's a negative 60 right there. Okay, so this is the effect of rotating by negative 6 degrees about the origin, the vector negative 5, 12. So the result is the answer. So cosine of negative 60, cosine of negative 60 is just 1/2. That's 1/2. And then sine of negative 60 is negative root 3 over 2, but it's a negative of that. So this is root 3 over 2. Sine of negative 60 degrees is negative root 3 over 2. So, okay, and cosine of negative 60 degrees is 1/2. Okay, so that's your matrix. And so you're left multiplying negative 5, 12 by that matrix. And so then the result is a two-tuple, which are the coordinates of the resulting point after you rotate by negative 6 degrees with the origin. And so you get negative 5/2 plus 6 root 13, 6 plus 6 root 3 as the first component here. So you get negative 5/2 plus 6 root 3. And then the other component is 5 root 3 over 2. And then the other one is 6, so plus 6. Okay, and so that is the, that's it. Okay, so that's number 4. So, yeah, and so the way I expressed it is the same, right? So this, the way I wrote it here, I tried to write it as one fraction for each. This is the same as negative 5/2 plus 6 root 3 and 5 root 3 over 2. You divide by the 2 and separate the terms, and then you get plus 6, right? So the blue is how I wrote it on the whiteboard, and on the left, when I wrote the answer sheet, I combined them as one fraction, so it would be one number in each component, which I guess looks better, looks nicer. Either one is good, either one is right. Okay, so that's number 4. Okay, so 2, 4, and 5 we've done. Let's do number 3. Find bases for the null space and row space of A. So I'm quickly going to write down on my sheet here how to do it. Write it down and then write on the screen. Okay, so Okay, so let me write okay, so first let me go to, so this is number 3. Okay, so you have your original matrix. Three, -2, 1, 4, -1, 0, -1, 0, -1, -2, -1, 0, 2, 3, 5, 7, 8, 0. Okay, so after row reducing, you get this. Okay, so those are just zeros. Okay, so okay, good. So now here are your leading ones. Okay, so this is in reduced echelon form. Yes, I just got to reduce echelon form. So the first 2 rows of that matrix will then correspond with, so this tells you that the row space of your matrix is spanned by the first 2 rows. So a basis for the row space of A is the first 2 rows of A. Okay. You're asking me how did I get that to reduce echelon form? Um, okay. What do you mean? What do you mean? Oh, okay. Okay. So you got this to reduce. Get this to reduce echelon form. The first 2 rows are your rows with leading ones. Those correspond with the first 2 rows of your matrix. And so then that means that either way. Okay, so the way I chose it here was that my 2 resulting Okay, there's more than one answer. So, so here, when I got this to reduced row echelon form. Before I got to reduced row echelon form, I got to just row echelon form. And so when I got to row echelon form, it was 1, 4, 5, 6, 9, 0, 1, 1, 2, 0. Okay, so this is now in only row echelon form, but that's still good enough. So that's good enough. So when you get your matrix to row echelon form, the locations of the leading ones are where they are. They don't change. And so now that you know where the leading ones are, you have that the first two rows will form a basis for the row space of your original matrix. So you have your original matrix, know when to form, you get to row echelon form. The rows with leading ones are the rows. Those rows will form a basis for the row space of the original matrix. And so in the solution sheet there, that's the way I did it when I did the solution sheet. I gave those two vectors as a basis for the row space of A. So that's that answer. Okay, and so now the basis for the null space of A. So the null space of A is the solution space of AX equals 0. Okay, so the solution space of AX equals 0. So I augmented the matrix in the beginning. That way I could do this. So this is in row echelon form. And so like I said, I also got into reduced row echelon form. So I'm going to put it back to reduced row echelon form. That way I can talk about the next step. So in reduced row echelon form, this matrix is this. Okay, so in reduced row echelon form, you have this. Now, so now the columns with leading ones. No, you can also do it reduced row echelon form. So there's infinitely many answers. I mean, they're not all, you can't write anything you want, but there's lots of choices for the answer. So if you got in reduced row echelon form, you could use these first two rows also as the answer. But you just need it in at least row echelon form. When you have it in reduced row echelon form, it is also in row echelon form. So any matrix in row echelon form, and there are infinitely many, any matrix in row echelon form, the rows with leading ones will form a basis for the row space of the original matrix. Okay, and so in the solution method, I chose only row echelon form because it's faster, and so I presented the solution that required the least amount of work and shortest amount of time. So on the exam, the best way is to take the original matrix, get it to only row echelon form, and then take the rows with leading ones. That will form a basis for the row space of the original matrix. Okay. But in the second part of the problem, I say find a basis also for the null space. And so when you want to find a basis for the null space, I now want to think of in reduced row echelon form. So here, the first two columns correspond with the two leading variables. Okay, so x1, x2 are leading variables. The free variables are x3, x4, and x5 because they correspond with variables that don't have leading ones in their columns. So I want to express each of these parameters. So I'm going to x3 as r, x4 as s, and x5 as t. Okay, so I'm expressing each of those three as their own parameters. And so now I'm going to solve for each of the other ones in terms of those parameters. So x1 is going to equal to negative r minus 2s minus t. x2 is going to equal to negative r minus s minus 2t. x3 is going to equal r. x4 is going to equal s. And x5 is going to equal t. So I've now found x1, x5 in terms of the parameters r, s, and t. And so to get the basis for the null space, I want to express a general vector in the solution space of AX equals 0, x1, x2, x3, x4, x5, as a linear combination with coefficients r, s, and t. This is equal to r times negative 1, 1, 0, 0, plus s times -2 -2, -1, 0, 1, 0 plus t times -1, -2, 0, 0, 1. Okay, so I've now expressed the solution space to ax equals 0 um, in this way. And so now I have a linear combination of these three vectors. So these three vectors form a basis for the null space of A. So this vector, this vector, this vector, those three vectors form a basis for the null space of A. And so we go here. That's it. -1, -1, 1, 0, 0, 1. Good. -2, -1. Yeah, that's it. Okay, so then now that's the basis for the null space of A. And so that's number 3. Okay, so then that's number 3. So I went through 2 through 5, and then I will go over number 1 now. The question was find bases for the null space and real space of A. So the question is asking you to find in this part, it's find a basis for the null space of A. A basis is a set, right? And so I have the set up here, right? So I have that there and that there. So I have it in, so I have it in the parentheses. So I'm expressing a basis as a set, which it is, right? It's not just ordered. Now you could say the basis formed by, if you said the eigens, these three vectors form a basis for the eigenspace of A, right? That would be fine. But the easiest way for me to explain it would be to just explicitly write what the basis is as an answer, right? Because I'm explaining to you what it means. So I wrote the answer down as B prime equals that set with those three vectors in it is a basis, because it's the most straightforward way to explain to the answer, right? That I'm asking you for a basis. A basis is a collection or set of basis vectors. We found the basis vectors, and so I just put them in a set, and that's the answer. So I would say that's the easiest way for you to write the answer too. That when you find the basis vectors, just put them in a set. That's a basis. You're welcome. Okay, so that's 2, 3, 4, and 5. So hopefully, I'm going fast, but this is recorded, so I guess you could watch these videos again a lot if you need to. Okay, but I'm covering everything, so that's the goal. Okay, the goal is so that everything's in this video somewhere. Okay, I think so. I'm trying to cover as much as possible in a short amount of time. Okay, so now number 1. Write the vector V as a linear combination of the vector of those 4 vectors. Okay. So I'll go through it, but now if you look at the answer sheet, you can see what's happening here. I'm taking a coefficient for each of the 4, and if you multiply each of them by those numbers, you add the products, you get that vector, right? So 2 minus 1 plus 8 minus 4, first component, you get, right? Okay, so but the question is, it's just calculations, so I'm just going to do it again. And just get it perfect this time. Okay, hopefully perfect this time. Okay, so give me a minute. I'm gonna do this again. 5, 0. Okay, so once I get this written down, I guess we'll be done. Okay, good. Okay, so now, all right. All right, so for number one, okay, so for number one, I guess start from the beginning. Okay, so you want to express this vector as a linear combination of those four vectors, right? So that means that you're going to have the vector 5, 3, 0 is equal to C1 times the first vector plus C2 times the second vector plus C3 times the third vector plus C4 times the fourth vector. Okay, and so then you get expressions for the first, second, and third on the right side and the left side. So that means that you then end up with a single matrix where you have 2, 1, 8, -4, 0, 4, 1, 6, 1, 3, 1, 1, partitioned by 5, 3, 0, right? And so you want to find the coefficient C1, C2, C3, and C4 with that augmented matrix. All right. So you get this to you reduce this matrix. And so if you reduce this matrix, you get this to 0, 0, 1, 6/29, 35/29. 0, 1, 1/4, 3/2, 3/4, 1, 1/2, 4, -2, 5/2. Okay, so you get that, reduce it to that. Now, look at this term. You have a 6/29 and you have a 35/29. So make C4 equal to 1. Make this a 1. That way you get rid of 6/29, and then C3 is also equal to 1. Okay, so now if C4 is 1, then that means C3 is 1. So once C3 and C4 are 1, then when you solve for C2, you get that this is 1/4 and 3/2. So then you subtract both of them from 3/4. And so when you subtract both of them from 3/4, it's just 1. Each of them are 1. So you have 1/4. So you have 6/4 plus 1/4 is 7/4. 3/4 minus 7/4, 6. So you have 2. So you have 6/4 plus 1/4 is 7/4. 3/4 minus 7/4 is minus 4/4 is minus 1. So the C2 is minus 1. And then you just solve for C1. And so then this is a minus 1. So this is a minus 1/2 plus 4 minus 2. So you get 2, you get 1.5, you subtract, that's 3/2. 5/2 minus 3/2 is 2/2, which is 1. So C2 is 1. And so one possible answer is C1 is 1, C2 is minus 1, C3 is 1, C4 is 1. Because when you get to this step, stop reducing it and get C4 equal to 1. And then C3 is also 1. And then C2 is minus 1. And then C1 is 1. So the trick of the problem is not to get it to reduce echelon form. You stop there and you solve the coefficient. There won't be, the test is not going to have a problem. I don't think like that. Okay, so that 1 minus 1, 1, 1. 1 minus 1, 1, 1. So that's the answer I presented in it. But there are infinitely many answers to this problem. This is just one of them. This one is the one I did because you don't have to get to reduced echelon form. When you get there, you set C4 equal to 1, and then that makes C3 equal to 1, and then you just use back substitution. The method back substitution means that instead of finding the solutions to all of them individually at the end, you find, you want to do row echelon form. When you get to row echelon form, You can use back substitution, meaning that meaning C4 can be anything you want, because when you get in Roche-Echelon form, you have 3 leading ones and 4 variables. So you have 1 free variable. So it's a parameter and it becomes anything you want. So the fourth C4 can be anything. You can choose it to be any value you want, but then that will determine the values of C1, C2, and C3. So if you choose C4 to be 1, then C3 is automatically 1, and then C2 is automatically -1, and then C1 is automatically 1. So you don't keep reducing the matrix. You just, this is actually going to be done pretty fast if you see this trick. If you use back substitution, the problem is easy or easier. If you don't use back substitution, it becomes hard, okay? Because the calculations start getting really bogged down. So that's why I forgot about back substitution. It is a method to solve. So sometimes the best way to do it is to not solve the entire matrix, instead to get a particular value and then back substitute to get the other value. Okay, and so that is the entire review sheet. Okay. Do you mean for number 1, or? Okay, so what I did was I got it to Roche-Echelon form, so you get that. Okay, so the columns of that matrix, right, correspond with the coefficients C1, C2, C3, and C4 at the bottom. So in the 4th column, I have a 6/29, right? That 3rd row of the matrix means 0 C1 plus 0 C2 plus 1 C3 plus 6/29 C4 is equal to 35/29. So that means if I set C4 equal to 1, then I can subtract the 6/29 from both sides, and I get that C3 is equal to 1. You see that? Because 35/29 minus 6/29 is 29/29, which is 1. So if C3 equals 1, if I set C4 equal to 1. Does that make sense? Faison, does that make sense? Okay, so now that I have C3 and C4 both 1, in the 2nd row of the matrix, the one row right above it, I have that C2 is equal to 1/4 C3, which is now 1. So C2 equals 1/4. I mean, C2 plus 1/4 plus 3/2 equals 3/4. And I just solve for C2. And so when you solve for C2, you get C2 equals -1. And now I've solved for C2. This is called back substitution. Then I go to the row above it, and I plug in C2 equals -1, C3 equals 1, and C4 equals 1. And I just solve for C1, and I get 1. Does that make sense? Okay, so I keep this problem on the review sheet. I think because there's something this problem does that other problems don't. This problem you really should use back substitution. It's hard to find a problem where back substitution is the way to do it. Normally, you might just do reduce Roche-Echelon form and you're done. In this problem, if you don't think back substitution, it becomes really annoying. So, sure. Okay, sure. So 4.8, problem 12. Sure. Okay, so all solutions on the whiteboard for /video for review sheets for practice test. Okay, so you may also need to look at the video for some of this. Okay, so 4.8, number 12. Okay. 12. Okay, so 4.8, number 12, it says let T be from R2 to R3, be the linear transformation defined by the formula. Find the rank of the standard matrix for T, find the nullity for the standard matrix of T. Okay, good question. Okay, so your matrix transformation is x1 plus 3x2, comma, x1 minus x2, comma, x1. Okay, so that's your That's your linear transformation. This is from R2 to R3, and it's R2 to R3 because you're plugging in x1, x2. You're plugging in a 2-tuple, and the output is a 3-tuple. Okay, so this is a function from R2 to R3. So in part A, you want to find the rank of the standard matrix. So you want to find the rank of the standard matrix for T. Okay, so what this matrix is doing is that your input is the vector x1, x2. And you're left multiplying it by the standard matrix for T. And the effect, the result is this matrix. So the result is x1 plus 3x2, x1 minus x2, and x1. Okay, so this bottom matrix is 2 by 1. And this matrix is 3 by 1, right? So the matrix you have to left multiply this by, but the inner entry would be the same. So it would be a 2 here, but it would be a 3 here. Okay, so the input of this transformation is x1, x2, and the output is this vector here. And so you want a 3 by 2 matrix. That's this. Okay, so you have a 3 by 2 matrix. I'm just going to try and line this up better. I'm going to test you don't concerned about this lining up. Okay, so now, okay, so the input is a 2 by 1 vector, the output is a 3 by 1. And so that means that when you fill in the gap here, you need to multiply this matrix by this matrix to get 3 by 1. The inner entry has to be the same, so it's a 2, and the outer, this has to be this one. Right, so this entry here corresponds with this entry here. And this entry here corresponds with this entry here. And because you started with this one, that means this one has to be the same. Okay, so I'm matching the colors here. So this one is this. Well, this one will be here. This one will be here. And so you get these two values from this and from this. Okay, does that make sense? So I know the size of this. This is the standard matrix for T. So now, if I want x1 plus 3x2, right, then I would take a 1 and a 3 here, because then 1 and 3 times this would be 1x1 plus 3x2 would give you this. 1 and a minus 1 here would be 1x1 minus 1x2 would give you that. And then this would be a 1x1 plus 0x2 would give you x1. Does that make sense? That's how you find the standard matrix for T. So far, we have that the standard matrix for T is this. Okay, the standard matrix for T is just the matrix that represents, is expressing this function as a matrix transformation, left multiplication by a matrix. Okay, so that's your standard matrix. And so the question is, find the rank of that standard matrix. The rank, remember, the rank is the rank of the matrix is the dimension of the row space or column space. Okay, both equal. Okay, so the rank of a matrix is the dimension of the row space or column space, which are both equal to the same number. Okay, so we can find the dimension of the row space. So to do that, we just want to get this matrix to row echelon form and see how many rows have leading coefficients, leading ones. Okay, so now I get this matrix to reduce echelon form. And so here's a 1, and here's it's a row echelon form. I add -1 times this to this, and I get 0, -4, and add -1 to that. 0, -3. Okay, I already see it, but I'm going to just put in all the steps here. Okay, so if I multiply this by -1/4, I get that, and that stays the same. And I'm going to add 3 times that row to that, and it gets this. So this is in row echelon form. Does that make sense? Does it make sense how this would go? This would be the matrix in row echelon form. Okay, so this is a matrix in row echelon form. So the number of rows with leading ones is the number of rows in any row echelon form of the original matrix with leading ones is the dimension of the row space, which is the rank of the matrix. So the rank of the matrix is 2. Okay, the rank of the matrix is 2. It's the dimension of the row space. It's the number of leading ones in the matrix in row echelon form. Does that make sense? The rank is the dimension of the row space of the original matrix. And so by getting the matrix to row echelon form and finding the number of leading ones there, you're finding how many vectors you need in order to express all linear combinations of the rows of the matrix as a linear combination of a certain number. So we only need two vectors to the basis for the row space consists of 2 vectors. Okay. Okay, so the rank of the matrix is 2. And for part B, you want to find the nullity of the standard matrix for T. So we have a theorem that says the rank of a matrix plus the nullity of that same matrix is equal to the number of rows n of a matrix, right? So given n by n matrix A, we have that the rank of A plus the nullity of A is equal to n. So here given a matrix A with n columns, given a matrix A with n columns, we have that the rank of A plus the nullity of A is equal to n. So here we have n equals 2 columns. So the rank of A, which is 2, plus the nullity of A, which we want to find, is equal to number of columns, which is 2. So that means that the nullity of A is equal to 0. That makes sense? Okay, so this is an important equation. If you have a matrix with n columns, the rank of that matrix A plus the nullity of that same matrix A is equal to n, the number of columns of that matrix. We found the rank, 2 plus the nullity of A is equal to 2. So nullity of A is 0. And so now I found both the rank and the nullity of the standard matrix for T. And so before that, I found the standard matrix for you, and I explained the steps to getting the standard matrix and then finding the rank and nullity of that matrix. Okay, other questions? Section 4.9, number 26. Okay. So for 4.9, number 26, it says the orthogonal projection of 1, 2 onto the line that makes an angle of pi/4 with the positive x-axis. Sure. Okay, so 4.9, number 26. Okay, so okay, I did this on the other. Okay, so 4.9, number 26. So 4.9, number 26. Okay, so looking at a picture of what's happening here, what you have. Okay, so let's say you have the XY plane, x-axis, y-axis. So you have a line that makes an angle of 45 degrees with the positive x-axis. So that's this line, right? So this is the line. Is it name? No, okay, there's no name. Okay, it doesn't matter. So now this is the angle, this is 45 degrees or pi over 4 radians. Okay, so that's your line. And you want the orthogonal projection 1, 2 onto the line. So 1, 2. So if you were here at 1, let's say this is 2. Let's say you have this point 1, 2. And you want your orthogonal projection of point onto that line. What that means is you're going to go from this point to the line in the fastest way possible, meaning in the perpendicular direction. And the foot of that line segment I drew, that is the orthogonal projection of the point onto that line. Does that make sense? Okay, so that's just visually what it means. So we'll keep going. Okay, so if you take that point and you take its orthogonal projection onto that line, you're going to the foot of that line segment, which that line segment is in the perpendicular direction of the line. Okay, and so the question is just how you know, how you find that. And so there's just a formula. And so the formula is just right before, it was in the class lesson 2 in the book. If you just go to back, if you go okay, so in the book, it's on page 169. It's also in the class notes. But in the book, if you go to page, not 160, page 267, and it's at the top of the page, and it's equation 4 at the top. Okay, and so that equation is what you use. So P theta is given to you. P theta is the matrix that you use in this example. And so they write it in 2 different ways. They're both equal. One way they write, I'll go with this way, is cosine squared theta, 1/2 sine theta. The best way to do is just remember it. You would just remember this matrix, okay? And so in the lesson, I gave you tables and I gave you values. So you just need to know those. There's a lot more in the book. You don't need to know anything in the book that I didn't go over in class. So you need to know the standard matrices for the ones I went over in class. So I went over this in class. So this is the matrix for cosine squared theta, 1/2 sine 2 theta, 1/2 sine 2 theta, sine squared theta. And so the theta is this 45-degree angle that the line is making. That the angle theta is determining the line that you're taking the orthogonal projection of it onto. So this line is completely determined by just the value of theta. So this matrix is determined by theta. And so all you have to do is plug in theta equals 45 into that matrix. And so you take p sub 45 degrees, you get cosine squared of 45 degrees, 1/2 sine of 2 times 45 degrees, which is 90 degrees, 1/2 sine of 90 degrees, and sine squared of 45 degrees. And so that's your matrix. And so you're left multiplying your starting vector. Your starting vector was 1, 2. And so if you left multiply your starting vector by this vector, the resulting vector is the effect of taking that vector and projecting it onto the line, that line, which is an angle of 45 degrees from the x-axis. That makes sense? So you just you multiply them and you get the answer. Cosine of 45 degrees is root 2 over 2. So squared is 2/4 or 1/2. So cosine squared of 45 degrees is 1/2. Cosine of 45 degrees is root 2 over 2. And so when you square it, you get 2/4 or 1/2. So that's 1/2. Sine of 90 degrees is 1. So 1/2 times 1 is 1. So that's also 1. 1/2 times 1 is 1/2. That's 1/2. Sine of 45 degrees is also root 2 over 2. So sine of 45 degrees, that's where sine and cosine are the same. Sine of 45 degrees is root 2 over 2, and squared is 1/2. So actually every entry is 1/2. And you multiply it by 1, 2, and the resulting vector is 1 plus 1/2 plus 1, which is 3/2. And the other one is also 1/2 plus 1, which is 3/2. The answer is 3/2, 3/2. That make sense? You're welcome. Okay, so which one we just did? We just did 4.9, number 26. So you also, it's good that you have questions. 4.6, number 6. 4.6, number 6. Okay, so 4.6, number 6. So this is the change of basis. Okay, I'm not surprised you asked about this. Okay, so consider the bases B, which is P1, P2, and B prime equals Q1, Q2 for P1, where that's at. Find the transition matrix from B prime to B. Okay, this is a homework question, right? In a test question, I would not ask a question with this much work in it, okay? But as far as a homework problem, this is a good homework problem because it means that you have to practice doing transition matrices, which is a lot of calculations. So it's calculations that you need to do in order to you need to experience them. Number 3, part A. Wait, what? Wait, you asked about 4.6, number 6, right? Well, I'm looking at 4.6. I answered everything else, and I'm up to 4. Well, I don't know what you mean. What's number 3? What do you mean by number 3? Where you asked about number 6? Where it was a typo? You said 4.6, number 6. Oh no, I mean it doesn't make any difference. I'm saying the same thing for number 3. Yeah, the same number 3 and number 6. The same comment about both. So I'm saying just don't worry. The test question would not take this much work. But what I mean is that for me to explain it to you, it might take a little while. But I have to give you this problem for homework because you have to be exposed to this kind of a question. It's just not okay. Anyway. Okay, so for number 6, it said you wanted to do number 6 because you asked about it, right? So number 6, you want to do number 6, right? That's better. I'd rather do numbers. Okay, so consider these bases, B and B prime. Okay, so find the transition matrix from B prime to B. Okay, I think I'm going to have to do this on the whiteboard again. Okay, so 4.6, number 6. So this is 4.6, number 6. So for 4.6, number 6, we have a basis B consists of P1, P2, and you have a basis B prime, which consists of Q1, Q2. And for P1, polynomials of degree at most 1. So P1 is equal to 6 plus 3x. P2 is equal to 10 plus 2x. Q1 is equal to 2. Q2 is equal to 3 plus 2x. So find the transition matrix from B prime to B. So in order to find the transition matrix from B prime to B, you want to take each basis vector in B and write it as a linear combination of the basis vectors in B prime. Let me write that. Okay, so to find the transition matrix from B prime to B, you need to express each basis vector in B, as a linear combination of the basis vectors in B prime. Okay, so to find the transition matrix from B prime to B, you first, I should say first because it's not the only thing you need to do. You first need to express each basis vector in B as a linear combination of the basis vectors in B prime. Okay, so no, I don't want to do that. Okay, good. Now, okay, each basis vector in B. So you have P1, which is 6 plus 3x. We're going to write it as a linear combination of the basis vectors in B prime. So that's Q1, which is 2, plus C2 times Q2, which is 3 plus 2x. Okay, so I'm expressing P1, a basis vector in B, basis B, as a linear combination of the basis vectors in B prime, Q1 and Q2. And so this is equal to 2C1 plus 3C2 plus 2C2x. Okay, but now notice that here I have a 3x and here I have a 2C2x. That means that 2C2 is equal to 3. So that means C2 is equal to 3 halves. Right? C2 is equal to 3 halves. And so since C2 is equal to 3 halves, that means that this expression is equal to 2C1 plus 3 times C2, 3 times 3 halves, which is 9 halves. And this is plus, now I have 3x here, right? So I have 2C1 plus 9 halves is equal to 6 plus 3x. So I already took care of the 3x. Now I have the 6, and this is equal to this. So 6 is equal to 2C1 plus 9 halves. 6 is equal to 2C1 plus, that's 4.5 plus 4.5. So that means that 1.5 is equal to 2C1. So that means C1 is equal to 3/4. C1 is equal to 3/4. So what that means is that P1 is equal to 3/4 Q1 plus 3 halves Q2. Does that make sense so far? I wrote the first basis vector in B as a linear combination of the two basis vectors in B prime. Okay. Okay, so that was that. Now I want to express the second basis vector in B, which is P2, as a linear combination of basis vectors in B prime, Q1 and Q2. So P2 is equal to 10 plus 2x. And I'm going to reuse my notation. So even though the 3C2, where's the 3C2? Oh, 3C2, yeah, it became 9 halves. It was still, yeah, because the 9 halves is a number, right? You have the 3x. You can only combine numbers and x's terms, right? The terms in the teal are the numbers. The 3x is x's, right? You can't add apples and oranges, right? I have 2C1 plus 9 half apples, and I have 3 oranges, 3 x's. Make sense? So 10 plus 2x is equal to C1 Q1, or C1 times 2, plus C2 times Q2, which is 3 plus 2x. So this is equal to 2C1 plus 3C2 plus 2C2x. And so then that means that the 2x is equal to, again, the 2x is equal to the 2C2x. That means that 2 is equal to 2C2. That means C2 equals 1, right? So C2 equals 1. And so then that means that since C2 equals 1, that means I have 2C1 plus 3 times C2 plus 3 plus, and I chose C2 appropriately so that I get a plus 2x here. And so that's done there. So now you have a 10 and you have a 2C1 plus 3 here. They're equal. That means the 10 is equal to 2C1 plus 3. So that means that C1 is equal to 7/2 or 3.5. Okay, so C1 is equal to 3.5. Okay, so P2 is equal to 7/2 Q1 plus 1 Q2. Okay, so I've now expressed P2 as linear combination of the base vectors in B prime also. So now that I've done that, I want to find the transition matrix from B prime to B. So the transition matrix from B prime to B is just the columns are from the coordinates of each of those basis vectors relative to the new basis B prime. So the coordinates here, because P1 is written as 3/4 Q1 plus 3/2 Q2, and Q1 and Q2 are basis vectors for the basis B prime. Coordinates of P1 relative to B prime is equal to 3/4, 3/2, because those correspond with the coefficients of Q1 and Q2. Here, I've expressed P2 as equal to, this is relative to the basis B prime. I've expressed it as 7/2 Q1, 7/2 Q1 plus 1 Q2. That means coordinates of P2 relative to the basis B prime is equal to 7/2, 1. So that means the coordinates of P1 and P2 relative to the basis B prime, those coordinates correspond with the columns of the transition matrix from B prime to B. So the first column is going to be the coordinates of P1 relative to B prime, which is 3/4 and 3/2. And the second column is going to be the coordinates of P2 relative to B prime, which is 7/2 and 1. So that's the transition matrix from B prime to B. That makes sense? That makes some sense? So Benjamin, okay, Erkan, you're saying it makes sense. Benjamin, you're saying would we also be able to find transition matrix by doing reduced Rescale form on 2 matrices? What 2 matrices? I don't think so. I'm not sure what you mean. You'd have to show me what you mean. It's possible you're talking about something that worked, but I feel like there may be, but I don't. It's not the way I do it, and so I think the best thing for me to oh, you mean equation 14? In the book, maybe on the book page, on page 233. It's when you have the new basis on the left and the old basis on the right, and you get it to reduce Rescale form. Yeah, you could do that. Yeah. We did that in class. Yeah. Yeah. If you want the transition from old to new, then you want the new basis on the left and the old one on the right. And the columns correspond with the basis vectors. So when it says new basis, it means the columns are the new basis vectors, and then the old basis, the columns are the old ones. Yeah, and then you get to reduce Rescale form. And then on the right side is the transition from the old to new basis. Yep. Yeah, you can do that too. Yep. I instinctively go to this method. Yeah, you can do that. That works also. Okay, so then B is just almost the same thing, but just reversed. So I don't know if you need me to do that. It's this essentially, just either method, just doing the opposite, expressing each, either you switch the left and right side. Okay, so to find the coordinate vector, right? So compute the coordinate vector of P relative to B, where P is equal to that, right? So to compute the coordinate vector, you want to express P as a linear combination of the basis vectors for B, right? So if you want to find the coordinate vector of P relative to B, right? Then what you want to do is this is equal to, let's say, C1 comma C2, such that P is equal to C1. Now the basis for B, looking back, the basis for B is P1 comma P2. Okay, those are the two basis vectors for basis B. So P is equal to C1 P1 plus C2 P2. So if you can find constant C1 C2 such that you can express P in this way, then they're the components of the coordinate vector of coordinates, coordinate vector P relative to B. Does that make sense? So if you have B, which has these two basis vectors, you want to express your polynomial P as a linear combination of P1 and P2. The coefficients of P1 and P2 respectively are the coordinates of P relative to that basis. Make sense? And so that's what you have to do. So if I were to do this, it would be another 10 minutes of me just getting another vector to a linear combination of two other vectors. It's like the same procedure, just done over and over again for different problems. You know what I mean? You're expressing a vector as a linear combination. And so the goal is to find C1 and C2. Okay. And that's that. Is that good? Can we stop there? Okay, what's the question? 4.4, number 9. Okay, so for 4.4, okay, so 4.4, number 9, you want to show that they do not form a basis for M sub 2, right? A basis is a set that spans and is linearly independent, right? So one of two things either fails. Either it doesn't span M sub 2, or it's not linearly independent. Okay. Now, if it was linearly independent, then that would mean it would have to be a basis because you have 4 vectors already. And we have a theorem that says that if the dimension of your space is n, and you look at a set of n vectors, then you only need one of two things to be true: linear independence or spanning, and then it applies to the basis. So I could tell you that the problem's telling you it's not a basis. So I rate backwards logic, it can't be linearly independent. So the fastest conclusion I reach is, well, you could show that they are not linearly independent. Okay. Now, if you look at the first, third, and fourth matrices, you see how they have zeros in different positions, different entries, right? The first, third, and fourth. So the first, third, and fourth matrices are linearly independent, right? So if you just looked at the first, third, and fourth, that forms a linearly independent set. That makes sense? So I know through backwards logic, since it's not a basis, they can't be linearly independent. And I know the first, third, and fourth are linearly independent, which means that the problem is the second matrix. The second, by adding the second matrix, you no longer have, it can't be that you still have a linearly independent set. So to show that this does not form a basis, what you can do from all the things I just said, you could then say, after all the things I just said, that you can show that the second matrix is a linear combination of the first, third, and fourth matrices. That will mean that the 4 matrices together do not form a linearly independent set. then once you know that, it cannot be a basis. That makes sense? Okay, so what you have to do is show that the second matrix is a linear combination of the first, third, and fourth. So you want to show that 2, -2, 3, 2. Do you want me to show you that, or is that good? You can just, it's like the same procedure as every problem. You're taking that matrix and you're showing it's a linear combination of the first, essentially there's no way around the fact that you just have to do this computations, and then you have then plus C3 times 0, -1, 1, 1. Okay, so well, okay, well now look at this. Now look at this. So this problem is getting like it's kind of a creative example. Now, if you have this one, all right, this one, and this one. Oh, okay, well, sort of. Okay, so if there's zeros in each of them, so that might make it easier. Okay, so you have this entry is C1 plus C2. This entry is -C2 minus C3. This entry is C1 plus C2 plus C3. This entry is C1 plus C3. Okay, so now you just solve the system of linear equations. 2 is equal to 2C1, -2 is equal to -2 minus C3. 3 is equal to C1 plus C2 plus C3, and then 2 is equal to C1 plus C3. And so that means that you have C1 plus C2 is equal to 2. You have -C2 minus C3 is equal to -2. You have C1 plus C2 plus C3 is equal to 3, and C1 plus C3 is equal to 2. And you solve that linear system for C1, C2, and C3, and you find that there is a solution, which means that then you're done. Okay, so I'm going to erase this, and so now you have the corresponding augmented matrix 1, 1, 0, 2. I wonder who came up with the names. Augmented matrix. Okay, 1, 0, 1, 2. Transformers. All right, so now you get. Okay, so now I'm just going to solve it. So now you get this multiplied by -1. Add -1 times the first row to the third row. There we go. That's good. And then I'm going to take -1 times n, that's the other one. Okay, so now right here, I see that C3 has to equal 1. Okay, so here, this tells you that C1 equals 1. This tells you that C3 is equal to 1. And now that C3 is equal to 1, you see by back substitution that this is telling you that C2 is going to equal 1. Because the C3 is 1. So 2 minus 1 is 1. So all three of them are 1. So now, maybe this might have been done. Oh, this guy. So if C2 is 1, C1 is 1, C2 is 1, C3 is 1, then you can express this matrix as a linear combination of those three matrices, which means that the set is not linearly independent, which means that it does not form a basis for M sub 2. Make sense? Okay. You're welcome. Okay. You're welcome. Okay, I don't know why. Yeah, there we go. Okay, so have a good night. And I'll see you on Thursday. Okay, I'm going to save the whiteboard. So the whiteboard is saved. You're welcome. You're welcome. I hope you do well. Do well. Okay. Do well. So and stay up for nothing. Have a good night. All right, see you Thursday.